There is something pulling us through space right now, not a metaphor, an actual gravitational anomaly, so massive it is dragging our entire galaxy toward it at hundreds of kilometers per second, and most people will never hear about it. But that pull is just one piece. Layer everything together, and you are moving through the universe at a speed your brain was simply never built to comprehend. If you have been moving this whole time, where exactly are you going? If understanding the universe at this level is what excites you, make sure to give this video a like. Now let's get started. Our planet spins on its axis once every 24 hours. Simple enough, right? But what that actually translates to in terms of speed is something most people never stop to really appreciate. If you are anywhere near the equator, somewhere like Brazil, Indonesia, or Kenya, you are rotating at roughly 1,670 kilometers per hour, 1,670. That is faster than a supersonic aircraft, faster than any military jet in active service today. The SR-71 Blackbird, one of the most remarkable flying machines ever built, had a top speed of about 3,500 kilometers per hour, and that was considered extraordinary. You, just existing on the surface of this planet near the equator, are already doing nearly half that speed without burning a single drop of fuel. Now, if you live further from the equator, somewhere like France, Canada, Argentina, or New Zealand, that speed drops a little. The Earth is a sphere, and the circles of latitude get smaller as you move toward the poles. So the spin stays the same, one full rotation per day, but the distance you cover per hour goes down. At the poles themselves, you are essentially turning in place. Rotating technically, but not really going anywhere. For most of humanity though, supersonic is the baseline. That is the floor, the slowest version of your motion through space, and you feel none of it. Not a single sensation, no wind, no pressure, no sense of movement whatsoever. That is because everything around you, the air, the oceans, the buildings, every blade of grass, is moving at the exact same speed in the exact same direction. There is no contrast, no frame of reference to measure it against. Physics is playing the most elegant trick imaginable, and your body is completely fooled. But here is the thing, this spin is the tiniest piece of the picture. It is a rounding error compared to what comes next. While Earth spins, it is also sweeping around the Sun in a massive elliptical path, and the speed at which it does that is genuinely staggering. Earth travels around the Sun at an average of approximately 107,000 kilometers per hour. That is about 29 to 30 kilometers every single second. In the time it takes you to snap your fingers, you have moved roughly 30 kilometers through space. In the time it takes you to blink, you have covered about 15 kilometers. Every breath, every heartbeat, every moment of your life, you are racing through the solar system at a pace that has no real human equivalent. This orbit is not a perfect circle. It is an ellipse, a slightly squashed oval, which means our distance from the Sun changes slightly throughout the year. Around early January, Earth reaches what is called perihelion, its closest point to the Sun, at about 147 million kilometers, and because of the way orbital mechanics work, we move a little faster at that point. Then, around early July, we reach aphelion, our farthest point, at about 152 million kilometers, and we slow down just a fraction. The difference in speed between these 2 points is not dramatic, but it is real and measurable. What this also means is that the seasons are not caused by our distance from the Sun. That is one of the most persistent myths in science education. The seasons happen because Earth is tilted on its axis about 23.5 degrees, so different parts of the planet receive sunlight at different angles throughout the year. When the southern hemisphere is tilted toward the Sun, it is summer down there and winter in the north. The distance from the Sun barely factors in. In fact, the northern hemisphere experiences its summer, when Earth is slightly farther from the Sun than usual. Distance is almost irrelevant. Tilt is everything. But back to the orbit. In one full year, 365 days, Earth covers a path of roughly 940 million kilometers around the Sun, nearly 1 billion kilometers in a single year, just to end up back where it started. Except it never actually ends up where it started, and this is something worth sitting with for a moment. Because the Sun is not standing still either. Our entire solar system, the Sun, all 8 planets, every moon, every asteroid belt, every comet swinging in from the outer reaches, is orbiting the center of the Milky Way galaxy. And it is doing so at a speed that makes Earth's orbital velocity look almost modest. The solar system travels around the galactic center at approximately 828,000 kilometers per hour, 230 kilometers per second, nearly 8 times faster than our orbit around the Sun. And yet, because the Milky Way is so incomprehensibly vast, even at that speed, one full orbit takes between 225 and 250 million years. Astronomers call this a cosmic year or a galactic year. And what that number actually means in historical terms is extraordinary. The last time our solar system occupied roughly the position in the galaxy that it does today, the Triassic period was just getting started on Earth. The very first dinosaurs were beginning to appear. The supercontinent Pangaea was still intact. 225 million years ago, and we are only now completing one single lap around the galactic center. Our solar system is estimated to be about 4.5 billion years old. In that time, it has completed roughly 20 of these galactic orbits, 20 laps around a galaxy 100,000 light-years across, 20 cosmic years of continuous, uninterrupted motion through space, and not once has the journey paused. You are on that journey right now, spinning at 1,670 kilometers per hour, orbiting the Sun at 107,000 kilometers per hour, and sweeping around the galactic center at 828,000 kilometers per hour. All simultaneously, all without any sensation of movement whatsoever. And here is something that will help put all of this into perspective. The video on the card above explores how long it would really take to travel 1 light year, and it breaks down exactly what these distances mean in real practical terms. If you want to feel the true scale of what we are talking about, that video pairs perfectly with this one. The link is in the description and pinned on the comments now. Everything we have covered so far, the spin, the orbit, the galactic rotation, those are the layers most people with a passing interest in astronomy have at least heard of. But here is where the story becomes something else entirely, because the Milky Way itself is moving, not just rotating, actually traveling through space, being pulled by gravitational forces operating at a scale that dwarfs anything we have discussed so far. There is a region of the universe, an enormous concentration of mass, that is drawing our galaxy along with dozens of others toward it at extraordinary speed. We have mapped its gravitational influence. We have measured the pull it exerts on everything around it. But because of where it sits in the sky, hidden behind the densest part of our own galaxy, we have only recently begun to understand what is actually there. So let's talk about the Milky Way itself, because our galaxy is not just sitting there, spinning peacefully in the void. It is moving through space with a sense of urgency that, once you understand it, makes the universe feel like a much more dynamic and restless place than most of us were ever taught. The Milky Way as a whole is hurtling through space at roughly 2,100,000 kilometers per hour. Relative to the cosmic microwave background, the faint afterglow of radiation left over from the Big Bang itself. That is the closest thing we have to a fixed reference point in the universe, and against that backdrop, Our galaxy is screaming through space at a speed that is almost impossible to put into human terms. But here is what makes this even more interesting. That motion is not random. It is not the Milky Way just drifting aimlessly through the cosmos. Something is pulling it, something enormous. And for a long time, astronomers knew something was there but could not see it, could not directly observe it, because it sits almost perfectly behind the thickest, dustiest, most star-crowded region of our own galaxy, a region called the Zone of Avoidance, where the sheer density of the Milky Way's disk blocks our view of whatever lies beyond. What lies beyond, as it turns out, is one of the most gravitationally dominant structures within our cosmic neighborhood. It is called the Great Attractor, and it sits roughly 250 million light-years away from us, in the direction of the constellations Centaurus and Norma. It is not a single object, it is not a supermassive black hole or a single galaxy. It is more like a region, a gravitational focal point, where an enormous concentration of mass is pulling everything in the surrounding area toward it. Galaxies, galaxy clusters, entire superclusters of galaxies, all flowing in its direction like water circling a drain. For decades after astronomers first detected its gravitational influence in the 1980s, the Great Attractor remained almost entirely mysterious. We could measure the way it was pulling on us. We could calculate roughly where it had to be based on the motion of galaxies in the region, but we could not see it. The zone of avoidance was in the way, and our optical telescopes were essentially useless for piercing through all that dust and gas and stellar crowding. That changed when astronomers began using X-ray telescopes and radio telescopes, instruments that can see right through the kind of dust that blocks visible light. And what they found was a massive supercluster of galaxies called the Norma cluster, along with several other significant galaxy concentrations, all sitting in roughly the location where the Great Attractor's gravitational center was predicted to be. It was a huge moment. Decades of gravitational detective work, confirmed by technology that sees the universe in an entirely different kind of light. But then, and this is where it gets genuinely mind-bending, astronomers realized the Great Attractor might not even be the ultimate destination. There might be something pulling on the Great Attractor itself. In 2013, a team of researchers led by astronomer Brent Tully at the University of Hawaii published a landmark study that fundamentally changed the way scientists understand the large-scale structure of the universe. Using a massive catalogue of galaxy velocities, measuring how fast and in which direction hundreds of thousands of galaxies were moving, they mapped out the gravitational boundaries of our cosmic neighborhood in a way no one had done before. What they discovered was that the Milky Way is not just a member of a small group of galaxies or even a modest cluster. We are part of something vastly larger. They named it Laniakea, a Hawaiian word meaning immeasurable heaven, and immeasurable is not an exaggeration. Laniakea is a supercluster of galaxies spanning roughly 500 million light-years across. It contains the mass of approximately 100 million billion suns, one followed by 17 zeros. It holds an estimated 100,000 galaxies, including our own Milky Way, the Andromeda Galaxy, the Virgo cluster, and hundreds of other galaxy groups and clusters, all bound together within a single enormous gravitational structure. And within Laniakea, everything flows. Not randomly, not chaotically, but in long, graceful streams. Rivers of galaxies all converging toward the gravitational heart of the supercluster. That heart is a region called the Great Attractor. So the Great Attractor is not some external force pulling on us from outside our cosmic neighborhood. It is the center of our supercluster. We live in Laniakea, and the Great Attractor is essentially Laniakea's gravitational core. Think about what that means for a moment. The address of our existence in the cosmos is something like this: You are on Earth, orbiting a star called the Sun in a solar system on one of the outer spiral arms of the Milky Way galaxy, which is a relatively small member of a group called the Local Group, which itself sits near the outer edges of the Laniakea supercluster, slowly being drawn, along with everything else in the supercluster, toward the gravitational center hundreds of millions of light years away. That is where you live. That is the full address. And every single layer of that address is in motion. Now, Tully and his team's work was extraordinary not just because it identified Laniakea, but because of how they identified it. Instead of just mapping where galaxies are, their positions in space, they mapped where galaxies are going. They used something called peculiar velocity surveys, which measure the motion of galaxies relative to the overall expansion of the universe. Strip away the expansion, and what you are left with is the gravitational flow, the way matter is being pulled by the underlying architecture of mass in the cosmos. And those flows revealed the boundaries of Laniakea, the way river basins define the boundaries of watersheds on Earth. Follow the water downhill, and it all ends up in the same river. Follow the galaxies through their gravitational flow, and they all end up converging toward the same point. It is one of the most elegant pieces of scientific reasoning in modern cosmology, and it completely reframed our understanding of where we are. But even Laniakea is not the end of the story, because Laniakea itself sits within an even larger context, the cosmic web, and the cosmic web introduces a layer of motion and structure that operates on scales so vast they begin to strain the very concept of distance. The cosmic web is the large-scale structure of the entire observable universe. It is a network of enormous filaments, long, thread-like structures made of dark matter and ordinary matter that stretch across hundreds of millions of light years, connecting galaxy clusters and superclusters like the strands of an impossibly large spider's web. Between these filaments are vast, almost empty regions called cosmic voids, bubbles of space where very little matter exists, some of them hundreds of millions of light years across. Our own Laniakea supercluster sits at the intersection of several of these filaments near the edge of a large void. And the galaxies within and around Laniakea are not just being pulled toward the great attractor, they are also participating in the large-scale flow of matter along the cosmic web, moving toward even larger concentrations of mass further out in the universe. One of these larger concentrations is a structure called the Shapley supercluster, or the Shapley concentration, located about 650 million light-years from us. It is one of the most massive structures in the observable universe, and there is strong evidence that its gravitational influence extends all the way to our corner of the cosmos. Some researchers believe the Shapley concentration is at least partially responsible for the overall direction of our motion through the universe, that its gravity is contributing to the flow that carries Laniakea, the great attractor, and everything in our cosmic neighborhood in a particular direction through space. So when you add all of this up, Earth's spin, Earth's orbit around the Sun, the solar system's orbit around the galactic center, the Milky Way's motion within Laniakea, and the broader flow of Laniakea itself through the cosmic web, you get a picture of motion that is layered, complex, and operating simultaneously across scales that range from the local to the almost incomprehensibly vast. And here is what is remarkable about all of it. None of these motions cancel each other out. They stack, they combine. Your actual trajectory through space at any given moment is the vector sum of all of them, a complex curving path through the universe that no human instrument has ever fully traced, and that changes constantly as each layer of motion evolves over time. You are not standing still in any meaningful sense. You never have been, you never will be. Every moment of your existence, you are a passenger on a journey happening at multiple speeds in multiple directions simultaneously, embedded in a universe that is itself expanding in all directions at once. And that expansion, the expansion of the universe itself, is the final layer, the deepest one, and it is the layer that breaks all the rules, because it involves a kind of motion that does not behave the way any of the others do. It is not caused by gravity. It is not caused by any force we fully understand. And in some parts of the universe, it is moving things apart faster than anything we have ever measured. That is where we are going next. And I promise you, the expansion of the universe is the part of this story that will make everything else we have talked about feel small. Let's talk about the expansion of the universe. Because this is where everything gets strange. This is where the comfortable, intuitive rules we use to understand motion in everyday life simply stop applying. And if you have ever heard someone say that the universe is expanding and just nodded along without really feeling the weight of what that means, this is the moment that changes. Start with this. When astronomers look at distant galaxies, they notice something remarkable. Almost every galaxy beyond our immediate cosmic neighborhood is moving away from us. Not just a few of them, not most of them, essentially all of them. And the further away a galaxy is, the faster it appears to be receding. A galaxy 1 billion light-years away is moving away from us roughly twice as fast as one that is 500 million light-years away. Double the distance, double the recession speed. This relationship was first described mathematically by Edwin Hubble in 1929, and it became the foundational evidence for the idea that the universe is not static, it is expanding. But here is where people often get the wrong mental image. When we say the universe is expanding, it is tempting to picture something like an explosion, matter flying outward from a central point, the way shrapnel spreads from a detonation. But that is not what is happening. There is no center, there is no edge. The expansion is not galaxies moving through space away from each other. It is space itself stretching, the fabric of the universe growing larger, carrying everything embedded within it along for the ride. Think of it like this. Imagine you draw a series of dots on a balloon, and then you blow the balloon up. Every dot moves away from every other dot simultaneously. No dot is the center, no dot is the origin point of the expansion. From the perspective of any single dot, all the others appear to be receding. The dots are not moving across the surface of the balloon. The surface itself is growing. The space between them is increasing. That is, in essence, what is happening to the universe. And this means that the recession of distant galaxies is not really motion in the conventional sense. It is not the same thing as a car driving away from you or a rocket launching into orbit. It is a stretching of the medium of space itself, and it does not obey the same rules that govern ordinary motion. There is no speed limit on how fast space can expand. The cosmic speed limit, the speed of light, applies to objects moving through space. It does not apply to the expansion of space itself. This distinction matters enormously, because when you start looking at galaxies that are extremely far away, billions of light-years distant, you discover something that sounds impossible. Some of them are receding from us faster than 300,000 kilometers per second. Some of them are receding from us at many times that rate. And yet, this does not violate any law of physics, because they are not moving through space at those speeds. Space between us and them is simply expanding so rapidly that the effective separation rate exceeds what we would normally consider the ultimate speed limit. There is a boundary in cosmology called the Hubble horizon, or sometimes the Hubble sphere. It sits at a distance of roughly 13.8 billion light-years from us, which, not coincidentally, is approximately the age of the universe in light-years. At that distance, the recession velocity due to expansion equals the speed of light. Beyond that boundary, galaxies are receding faster than light, and any signal they emit can never reach us. They are, in a very real sense, causally disconnected from us. Even if they shone with the brightness of 1 billion suns, their light would never arrive. The space between us is growing too fast for it to make the journey. The observable universe, the sphere of space we can actually see and detect, is everything within that boundary. But the total universe almost certainly extends far, far beyond it. How far? We genuinely do not know. It could be vastly larger than what we can observe. Some models of cosmology suggest it could be essentially infinite, and all of that space, visible and invisible, is expanding. Now here is the part that took the scientific community completely by surprise. For most of the 20th century, physicists assumed that while the universe was expanding, that expansion must be slowing down over time. Gravity, after all, is a universal attractive force. Everything pulls on everything else. So the combined gravitational pull of all the matter in the universe should be acting as a brake on the expansion, decelerating it, gradually pulling things back together, perhaps eventually reversing it into what cosmologists used to call the Big Crunch. That assumption turned out to be spectacularly wrong. In 1998, two independent research teams, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory and the other led by Brian Schmidt and Adam Rees at the High Z Supernova Search Team, were studying a specific type of exploding star called a Type Ia supernova. These supernovae are extraordinarily useful to astronomers because they always explode with roughly the same intrinsic brightness. That makes them what scientists call standard candles, objects whose true luminosity is known, so that by measuring how bright they appear from Earth, you can calculate exactly how far away they are. Perlmutter's team and Schmidt and Rias's team were both using these supernovae to measure the expansion rate of the universe at different points in cosmic history. The plan was to confirm the expected deceleration, to measure exactly how much gravity was slowing things down. Instead, they found the opposite. The distant supernovae were dimmer than they should have been, which meant they were farther away than expected, which meant the universe had expanded more between then and now than any decelerating model could account for. The expansion of the universe was not slowing down, it was speeding up. This discovery was so shocking, so contrary to everything physicists had assumed, that the teams initially suspected they had made an error. They checked their data, they reanalyzed their methods, they looked for systematic biases, calibration problems, anything that might explain the discrepancy without requiring the universe to be doing something that seemed to violate basic physics. But the result held. Both independent teams, using different data and different methods, arrived at the same conclusion. The expansion of the universe is accelerating. In 2011, Perlmutter, Schmidt, and Rias were awarded the Nobel Prize in Physics for this discovery, and it fundamentally changed cosmology because it meant something was driving that acceleration. Something was pushing the universe apart, actively working against gravity, counteracting the attractive pull of all the matter in the cosmos and winning. Whatever this something was, it was not nothing, and it was not any force or particle that physicists had previously identified. They gave it a name, dark energy, and that name is essentially an admission of ignorance. Dark energy is not a description of what this thing is. It is a label for something we know exists, know is real, know is dominant, and do not understand at all. Here is how dominant it is. When cosmologists calculate the total energy content of the observable universe, all the matter, all the radiation, all the gravitational potential energy, dark energy accounts for approximately 68% of it. Ordinary matter, everything you can see, touch, measure and detect, every star, every planet, every atom of every element in the periodic table, accounts for only about 5%. The remaining 27% is dark matter, which is its own profound mystery, but dark energy This unknown accelerating force makes up more than 2/3 of everything that exists. We are embedded in something we cannot see, cannot directly detect, and cannot explain, and it is the dominant feature of our universe. The current best mathematical description of dark energy treats it as a property of space itself, a kind of intrinsic energy that empty space possesses, sometimes called the cosmological constant. Einstein actually introduced the cosmological constant into his equations of general relativity in 1917 as a way of keeping the universe static. He believed at the time that the universe was neither expanding nor contracting, and he needed a term in his equations to counterbalance gravity. When Hubble's observations confirmed that the universe was actually expanding, Einstein reportedly called the cosmological constant his greatest blunder. He removed it from his equations. Then, 80 years later, the supernova teams discovered accelerating expansion, and the cosmological constant came roaring back. Except now it was not a fudge factor to keep things static. It was a real physical quantity, a measurable property of the universe. Einstein's greatest blunder turned out to be one of the most prescient things he ever wrote. But the cosmological constant comes with its own deep problem. When physicists try to calculate what the energy density of empty space should be based on quantum field theory, the incredibly successful framework that describes the behavior of particles and forces at the subatomic level, the answer they get is somewhere between 50 and 120 orders of magnitude larger than what is actually observed. That is not a small discrepancy. That is the largest disagreement between a theoretical prediction and an experimental measurement in the entire history of science. Something is deeply, profoundly wrong with our understanding of either quantum mechanics or gravity or both. This is one of the biggest open questions in all of physics. Why is dark energy so much weaker than our best theories predict it should be? Is it truly constant over time, or does it evolve? Could it eventually change, growing stronger or weaker, and alter the fate of the universe in ways we cannot currently anticipate? These are questions that the greatest minds in theoretical physics are actively wrestling with right now, and nobody has a satisfying answer. What we do know is the effect. The universe is expanding. That expansion is accelerating. Distant galaxies are being carried away from us faster and faster over time, and the ultimate consequence of that, if dark energy remains constant, is a future universe that looks very different from the one we inhabit today. In the very far future, we are talking timescales of trillions of years. Galaxies that are currently visible to us will eventually be carried beyond our Hubble horizon. Their light will no longer be able to reach us. One by one, across billions of years, the universe as seen from Earth will appear to shrink. Galaxies will fade. The cosmic web will become invisible to any future observers. Eventually, the only galaxies visible from the Milky Way will be the ones gravitationally bound to us. The local group and everything else will have disappeared behind the expanding horizon, gone forever from our observable universe. Future civilizations, if any exist, will look out into a universe that appears almost empty. They will have no observational evidence that the cosmic web ever existed, no way to detect the billions of galaxies that once filled the sky. They will look at the universe and see something that looks fundamentally different from what we see today. And they might conclude, wrongly, that the universe is small, simple, and mostly empty. The evidence of its true scale and structure will have been erased by the very expansion that created the conditions for their existence. In a way, we are extraordinarily lucky to exist at the particular moment in cosmic history when the universe is still observable in its full complexity. A few trillion years from now, the evidence will be gone. But even that picture, as dramatic as it is not the most extreme version of what the expansion of the universe might mean. because there are alternative models of dark energy that lead to scenarios even more radical than a slowly emptying cosmos. And one of them has a name that tells you everything you need to know about how it ends. The Big Rip. If dark energy is not constant, if it grows stronger over time, then the acceleration of the expansion could eventually increase without limit. And if that happens, the expansion would not just pull distant galaxies away, it would eventually overcome every other force in the universe. It would pull apart galaxy clusters, then individual galaxies, then solar systems, then planets, then atoms. Then in the final moments, the very fabric of space-time itself would be torn apart. Everything, every structure, every particle, every form of matter or energy would be shredded by the runaway expansion of space. Current observations suggest this scenario is unlikely. The data we have is more consistent with a cosmological constant, dark energy that stays roughly the same over time, than with a growing one, but the possibility has not been ruled out. And it is a reminder that the expansion of the universe is not a gentle, passive background process. It is an active, dominant force shaping the destiny of everything that exists. So where does all of this leave you? Right now, in this moment, you are spinning at 1,670 kilometers per hour. You are orbiting the Sun at 107,000 kilometers per hour. Your solar system is sweeping around the galactic center at 828,000 kilometers per hour. Your galaxy is flowing toward the Great Attractor as part of the Laniakea supercluster. And on top of all of that, you are embedded in a universe that is expanding in every direction simultaneously, accelerating under the influence of a force that makes up 68% of everything and that no one fully understands. You are in motion in ways that span more than 60 orders of magnitude in scale. From the spin of a single planet to the expansion of the entire observable universe. And not one of those motions, not a single layer, can be felt from where you are sitting right now. That should be astonishing. That should stop you in your tracks. The stillness you feel is one of the greatest illusions in nature. But here is the thing. We have not yet talked about what happens when you try to add all of these speeds together into a single number. When you try to answer the question the title of this video actually asks. Because it turns out that question is harder to answer than it sounds, and the reason it is hard is not because the math is complicated. It is because of something much deeper, something that cuts right to the heart of how the universe works, and what motion actually means at a fundamental level. We are getting to that. And when we do, the answer is going to surprise you. So we have been building toward this moment. Layer by layer, we have stacked up every component of your motion through the cosmos. And now comes the part where most people expect a single, clean, satisfying number, a grand total, one final speed that answers the question once and for all. And here is where the universe does something deeply humbling. It tells you that the question itself, how fast are you moving through the universe, does not have a simple answer, not because we lack the data, but because of something far more fundamental, something that sits at the very core of modern physics and completely reframes what motion means. Let's go back to basics for a moment. When you ask how fast something is moving, you are always, whether you realize it or not, asking how fast it is moving relative to something else, relative to the ground, relative to another car on the road, relative to the air around it. Motion is never absolute. It is always a comparison, a relationship between two things. This is not just a practical limitation. It is a deep truth about the nature of reality. There is no cosmic measuring stick nailed to the fabric of the universe against which all motion can be measured. There is no universal at rest. Physics does not have a preferred reference frame, a special vantage point from which all other motion can be judged as truly fast or truly slow. Every measurement of speed depends entirely on what you are measuring it against. This idea goes back to Galileo Galilei in the early 17th century. He recognized that the laws of physics work the same way whether you are moving at a constant speed or standing still. If you are on a smoothly sailing ship with no windows, there is no experiment you can do inside the ship that will tell you whether you are moving or stationary. The physics is identical either way. This principle, that the laws of nature are the same for all observers moving at constant velocity, became one of the foundational pillars of classical mechanics, and later of Einstein's special theory of relativity. Einstein took it further, much further. In 1905, he published his special theory of relativity, which built on Galileo's insight but extended it to include something Galileo could not have anticipated: the behavior of light. Einstein began with two postulates. First, the laws of physics are the same for all observers in uniform motion. Second, the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. That second postulate sounds simple, but its consequences are staggering. If the speed of light is constant for all observers, then space and time cannot be constant. They have to bend and stretch to accommodate that fixed speed. Two observers moving at different velocities will disagree about the length of objects, the rate at which clocks tick, and even the order in which events occur. These are not illusions or measurement errors. They are real physical differences, genuine disagreements about the nature of space and time that arise from the fundamental structure of the universe. Time passes more slowly for an object in motion than for one at rest, a phenomenon called time dilation. Distances appear compressed in the direction of motion, a phenomenon called length contraction, and the faster you move, the more pronounced these effects become. As you approach the speed of light, time slows towards zero from the perspective of a stationary observer, and distances compress towards zero in the direction of travel. These are not hypothetical predictions. They have been measured, verified, and accounted for in technologies we use every day. The GPS satellites orbiting Earth, for instance, have to correct for relativistic time dilation constantly. Without those corrections, your navigation app would accumulate errors of several kilometers per day. Relativity is not a theory, it is an engineering requirement. But what this means for our question, how fast are you moving through the universe, is that there is genuinely no single correct answer. Every answer depends on the reference frame you choose. Relative to the surface of Earth, you might be sitting still. Relative to the Sun, you are moving at 107,000 kilometers per hour. Relative to the galactic center, you are moving at roughly 828,000 kilometers per hour. Relative to the cosmic microwave background, that ancient afterglow of the Big Bang that fills all of space, our solar system is moving at approximately 370 kilometers per second, or about 1,332,000 kilometers per hour. That last number is particularly interesting because the cosmic microwave background is the closest thing we have to a universal reference frame. It fills all of space. It has no preferred direction. It is, in a sense, the most neutral possible backdrop against which to measure our motion. And relative to it, our entire solar system is moving at over 1,300,000 kilometers per hour in the direction of the constellation Leo. This motion was discovered in the 1970s through observations of the cosmic microwave background itself. When scientists mapped the temperature of this ancient radiation across the entire sky, they found a tiny but measurable asymmetry. One side of the sky appeared ever so slightly warmer, and the opposite side appeared ever so slightly cooler. The difference is tiny, just a few thousandths of a degree, but it is real, and it has a clear physical explanation. We are moving through the cosmic microwave background, and the motion causes a Doppler shift, the same effect that makes a passing ambulance siren sound higher pitched as it approaches and lower pitched as it moves away. The side of the sky we are moving toward appears slightly blue shifted, slightly hotter. The side we are moving away from appears slightly red shifted, slightly cooler. By measuring that asymmetry, astronomers could calculate our speed and direction through the universe with remarkable precision, so that is our best answer to the original question. Relative to the most universal reference frame we have access to, you are currently moving at approximately 1,332,000 kilometers per hour in the direction of Leo right now as you watch this. But here is something that makes even that answer more complicated. That speed is the speed of our solar system relative to the cosmic microwave background. It already incorporates our motion around the galactic center and the Milky Way's motion through space. But it does not separately account for all those layers in the way we have been describing them. The number is real and measurable, but it is a single combined value, a snapshot of our velocity relative to one particular reference frame. Change the reference frame, and the number changes. And then there is the expansion of the universe, which, as we discussed, is not really motion in the traditional sense. Distant galaxies are not moving through space away from us. Space is expanding between us and them, so their recession velocity, even when it exceeds the speed of light, is not something that can be added to our list of conventional speeds. It operates by different rules. It is not motion, it is geometry. The universe is not a place where things move. It is a structure that changes shape, and the change in shape carries things with it. This is one of the deepest and most unsettling truths in all of cosmology. We tend to think of the universe as a stage, a fixed backdrop against which events play out. But it is not a stage, it is a dynamic, evolving structure that is itself part of the story. Space is not empty, it is not passive, it has properties, it expands, it curves in the presence of mass. It can carry gravitational waves, ripples that travel through the fabric of space-time itself, produced by some of the most violent events in the cosmos. Gravitational waves were predicted by Einstein in 1916 as a consequence of his general theory of relativity, the extension of his special theory to include gravity and acceleration. He showed that massive accelerating objects, two black holes spiraling toward each other, two neutron stars colliding, would produce ripples in the curvature of space-time, spreading outward at the speed of light like waves on the surface of a pond. He predicted them, but he doubted they would ever be detected because the distortions they cause are almost unimaginably small. He was wrong about the detection. On the 14th of September 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected the first confirmed gravitational wave signal in history. The signal had been produced by two black holes, each roughly 30 times the mass of our Sun, spiraling together and merging into a single black hole 1.5 billion light-years away. The merger released more energy in a fraction of a second than all the stars in the observable universe emit in that same interval, and the ripple that reached Earth, after traveling 1.5 billion light-years through the expanding universe, distorted the fabric of space-time by a distance smaller than 1/10,000th the diameter of a proton. LIGO measured it anyway. That detection was one of the most extraordinary scientific achievements in human history. It opened an entirely new way of observing the universe. Before gravitational waves, astronomy was done almost entirely with electromagnetic radiation, visible light, radio waves, X-rays, gamma rays. Gravitational waves are different. They pass through everything. They are not absorbed or scattered by matter the way light is. They carry information about events and objects that are completely invisible to any conventional telescope. They are, in a sense, a new sense organ for humanity, a way of hearing the universe rather than just seeing it. And what gravitational waves reveal is a universe that is not just expanding and moving, but vibrating, shaking, producing distortions in the fabric of space-time that propagate across billions of light years. You are not just moving through space, you are embedded in a medium that trembles. Since that first detection in 2015, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events, merging black holes, colliding neutron stars, and potentially other sources still being analyzed. Each detection is a new data point, a new glimpse of violent events happening across the cosmos. And a space-based gravitational wave observatory called LISA, the Laser Interferometer Space Antenna, is currently in development by the European Space Agency. When it becomes operational, likely in the 2030s, it will be sensitive to gravitational waves at much lower frequencies than LIGO can detect, opening a window onto supermassive black hole mergers, the early universe, and possibly sources we have not yet imagined. But here is something worth sitting with. Every gravitational wave that passes through Earth, every ripple from a black hole merger billions of light years away, also passes through you. Your body stretches and compresses by an amount so infinitesimally small it can never be measured or felt. But it happens. The universe reaches out across billions of light years and momentarily, imperceptibly, changes your shape. You are not a passive observer of the cosmos. You are part of it. You interact with it. The fabric of space-time that carries gravitational waves also carries you, spinning, orbiting, hurtling, flowing through a universe that is itself in constant, dynamic, accelerating motion. Now, all of this, the relativity, the cosmic microwave background, the expansion of space, the gravitational waves, raises a question that cuts even deeper than the one we started with. If there is no absolute reference frame, if motion is always relative, if even space itself is not fixed, then what does it mean to be somewhere? What does it mean to be here, at this specific location in the universe? Because here is the thing. You can describe your position in the universe relative to Earth, relative to the Sun, relative to the galactic center, relative to the great attractor. But there is no absolute coordinate system for the universe, no cosmic GPS that gives you a fixed address. The universe does not have a center you measure your position from. It does not have an edge you can use as a reference point. Every position is defined only in relation to other positions, and since everything is moving relative to everything else, your position in any absolute sense is a concept that physics cannot support. This is not a failure of measurement or technology. It is a fundamental feature of the universe. The cosmos is not a place you are in. It is a set of relationships you are part of. Your location is not a point on a map. It is a description of how you relate to everything around you. And that relationship is always changing at every scale, in every direction, simultaneously. There is something profound in that, something that goes beyond physics into philosophy, maybe even into how we understand ourselves. We tend to think of ourselves as fixed, rooted to a place, anchored in a moment, but the universe does not share that intuition. From the perspective of the cosmos, you are a temporary configuration of matter and energy, moving through space at 1,000,000 kilometers per hour in multiple directions at once, embedded in a dynamic, expanding, vibrating structure that has been in motion since the very first moment of its existence. And yet, here you are, thinking about it, wondering about it, using 100 billion neurons, each one made of atoms forged in the cores of stars that lived and died before our sun was born, to contemplate the nature of the universe that produced you. That might be the most extraordinary motion of all, not the spinning, not the orbiting, not the hurtling through the cosmic web, but the fact that the universe through you has found a way to look at itself and ask, where am I going? How fast am I moving? What does it all mean? We are going to spend the next part of this journey looking at what the universe was doing before all of this motion began. Before galaxies, before stars, before atoms, in the first fraction of a second after the Big Bang, when the entire cosmos was smaller than a grain of sand and moving in ways that make everything we have discussed so far seem almost quaint. Because the very origin of all this motion, the reason anything is moving at all, is a story that starts at the very beginning of time itself. And it involves one of the most dramatic and strange events in the history of the universe, an event so violent, so rapid, so fundamentally transformative that it set the conditions for everything that has ever existed, including you. If you are enjoying this journey, make sure to give this video a like and subscribe. Every upload in this channel is designed to give you the kind of perspective that makes the world feel bigger and more fascinating. Let's go back to the very beginning. Not the beginning of Earth, not the beginning of our galaxy, the beginning of everything, the beginning of space, time, matter, energy, and motion itself. Because if you want to understand why you are moving through the universe the way you are, why anything is moving at all, you have to go back to the moment when the universe came into existence. And what happened in those first extraordinary moments is so strange, so violent, so utterly unlike anything in ordinary human experience, that even the scientists who study it professionally sometimes struggle to fully absorb what the mathematics is telling them. The Big Bang. You have heard the term. You probably have a mental image of it, a massive explosion, a fireball, matter flying outward in all directions. That image is wrong, not slightly wrong, fundamentally, deeply wrong in ways that matter enormously for understanding what the universe actually is and how it actually behaves. The Big Bang was not an explosion in space, it was an explosion of space. There was no pre-existing void into which the universe expanded. There was no outside that the universe burst into. Space itself, the very fabric of existence, came into being at the moment of the Big Bang, and it has been expanding ever since. There is no center to the expansion, because every point in space was at the center of the Big Bang. The Big Bang did not happen at a location. It happened everywhere simultaneously, because everywhere is what it created. This is one of those ideas that sounds like wordplay but is entirely literal. Cosmologists mean it precisely. The equations of general relativity, when applied to the early universe, do not describe matter expanding through a pre-existing space. They describe space itself expanding, carrying matter with it. The distinction is not semantic. It is the difference between a fundamentally finite and a fundamentally unbounded universe. It is the difference between an explosion with a center and an expansion with no center. And getting that distinction right is essential for understanding almost everything else in cosmology. So, what do we actually know about the very beginning? The honest answer is that our knowledge has a hard edge. There is a moment in time, approximately 10 to the power of -43 seconds after the Big Bang, a number so small it has no meaningful human analogy, called the Planck time. Before that moment, our current laws of physics simply break down. General relativity and quantum mechanics, the two great pillars of modern physics, are fundamentally incompatible with each other at those scales. Quantum mechanics describes the universe at the smallest scales, where everything is probabilistic, uncertain, and governed by the strange rules of wave functions and superpositions. General relativity describes gravity and the large-scale structure of space-time, and it is a smooth, continuous theory. When you try to apply both simultaneously to the conditions of the very early universe, where everything that exists was compressed into an almost infinitely small, almost infinitely hot, almost infinitely dense state, the equations produce nonsense, infinities that cannot be resolved, predictions that break down entirely. What this means is that we do not have a theory of quantum gravity, a framework that successfully unites quantum mechanics and general relativity, and without one, we genuinely cannot say what happened before the Planck time. We cannot describe the very first moment. We cannot answer the question of what caused the Big Bang, or what, if anything, existed before it. These are not gaps that will be filled by more careful observation or better telescopes. They are gaps that require a fundamentally new theory of physics, one that does not yet exist: string theory. Loop quantum gravity and several other frameworks are candidates for that theory. They each attempt to reconcile quantum mechanics and general relativity in different ways, and they each make different predictions about what the very early universe looked like. But none of them has yet produced a confirmed, testable prediction that has been verified by experiment. They remain mathematically rich but empirically unproven. The Planck time remains a wall beyond which science cannot currently see. But after that wall, from the Planck time onward, things become somewhat more tractable, and the story they tell is one of the most dramatic in all of science. In the first tiny fractions of a second after the Big Bang, the universe was unimaginably hot and dense. We are talking about temperatures in the quadrillions of degrees, conditions so extreme that the familiar particles of matter we know today could not even exist. The universe was a seething plasma of quarks and gluons, the fundamental building blocks that, at lower temperatures, would later bind together to form protons and neutrons. Everything was in constant, violent interaction. Particles and antiparticles were constantly being created and annihilated. Energy and matter were essentially interchangeable, pouring back and forth into each other in a continuous, frenzied exchange. And in this extraordinary environment, something happened that changed everything. Something that, without a shadow of a doubt, is responsible for the large-scale structure of the universe as we see it today, for the existence of galaxies, for the cosmic web, for the great attractor, for Laniakea, for the Milky Way, for our solar system, for Earth and for you. It is called cosmic inflation. The theory of inflation was first proposed by physicist Alan Guth in 1980, and it has been refined and developed by many researchers since then. What it proposes is this: in the first tiny sliver of time after the Big Bang, the universe underwent a period of extraordinarily rapid exponential expansion, not the gradual, steady expansion we observe today, something incomparably faster. In an interval of time estimated at somewhere between 10 to the power of -36 and 10 to the power of -32 seconds, durations so brief they make a billionth of a second feel like an eternity, the universe expanded by a factor of at least 10 to the power of 26. Some models suggest the expansion factor was far larger, possibly infinite. To give you some sense of what that means, if you took a single proton, something roughly 1 femtometer across, that is 1 quadrillionth of a meter, and inflated it by a factor of 10 to the power of 26, the result would be a sphere roughly 1 million light-years in diameter. The universe went from something smaller than a subatomic particle to something larger than a galaxy cluster in a fraction of a fraction of a fraction of a second. Nothing moved through space at that speed. Space itself inflated, and this is a crucial distinction because it means inflation did not violate the cosmic speed limit. The speed of light restricts how fast objects can move through space. It says nothing about how fast space itself can expand. During inflation, space expanded so rapidly that points which were once in contact, close enough to exchange information, to reach thermal equilibrium with each other, were suddenly separated by distances so vast that no signal could ever bridge them again. They became causally disconnected almost instantaneously. This solves one of the great puzzles of cosmology. When we look at the cosmic microwave background, that ancient afterglow of the Big Bang, we find that it is almost perfectly uniform in temperature across the entire sky. The The temperature varies by only about 1 part in 100,000 from one region to another. That is an extraordinary degree of smoothness. But here is the problem. Regions of the sky on opposite sides, separated by angles greater than about 2 degrees, are so far apart that in the standard Big Bang model without inflation, they could never have been in contact with each other. Light from one region could never have reached the other in the time available. So how did they reach the same temperature? How did they equilibrate? They could not have communicated. They should not look the same. Inflation solves this elegantly. Before the period of rapid expansion, all the regions that now make up the observable universe were in contact with each other. They had time to reach thermal equilibrium, to even out their temperatures. Then inflation stretched that tiny, equilibrated patch of space into something vast. The smoothness we observe today is the smoothness of that original pre-inflation patch stretched across the entire sky. But inflation does something even more remarkable than explain the smoothness. It also explains the structure, because the smoothness is not perfect. There are tiny fluctuations, those 1 in 100,000 variations in temperature, and those fluctuations are not random noise. They are the amplified imprints of quantum fluctuations from before inflation. In the quantum world, empty space is not truly empty. It seethes with fleeting fluctuations, tiny, momentary variations in energy density that pop in and out of existence on timescales so brief they seem almost fictional. Under normal circumstances, these quantum fluctuations are inconceivably small and have no macroscopic effect. But during inflation, they were stretched, blown up from quantum scales to cosmic scales. Tiny quantum ripples in the fabric of space-time became the seeds of large-scale structure in the universe. Those seeds, those microscopic fluctuations frozen into the cosmic microwave background, eventually grew. Under the influence of gravity, regions that were slightly denser than average attracted more matter. Over hundreds of millions of years, those overdense regions grew into galaxy clusters and filaments. The underdense regions became the great voids. The pattern of slight temperature variations we see in the cosmic microwave background today is a direct map of the initial conditions that gave rise to every galaxy, every star, every planet, and every living thing in the observable universe. The cosmic web, with all its filaments and voids and galaxy clusters, is the grown-up version of quantum fluctuations that existed in the first fraction of a second of time. You are the universe's quantum noise, scaled up by inflation and sculpted by gravity over 13.8 billion years. That is not a metaphor, that is what the physics says. Now, inflation has another consequence that is arguably the most mind-expanding idea in all of modern cosmology. If inflation happened, if space underwent this period of runaway exponential expansion, there is, in many versions of the theory, no reason it would have stopped everywhere at the same time. In what is called eternal inflation, quantum fluctuations in the inflation field, the theoretical energy that drove the expansion, would cause inflation to end in some regions while continuing in others. And the regions where inflation ends become what we call bubble universes, separate, self-contained regions of space with their own laws of physics, their own fundamental constants, their own structure. Meanwhile, the space between bubbles continues inflating forever, separating the bubbles from each other at rates that prevent them from ever interacting. This is the multiverse, not science fiction, not philosophy, a direct mathematical consequence of applying the same inflationary model that successfully explains the smoothness of the cosmic microwave background and the large-scale structure of the universe. The same framework that makes verified, testable predictions about things we can observe also predicts, almost unavoidably, the existence of an enormous, possibly infinite collection of universes beyond our own. Now, the multiverse is deeply controversial among physicists, The controversy is not primarily about whether the math produces it. It does. The controversy is about whether the multiverse is science. If other bubble universes are forever beyond our observational horizon, if no signal can ever reach us from them, if no experiment can ever detect their existence, then is the multiverse a scientific prediction or a philosophical consequence? Can it ever be tested? Is an untestable prediction meaningful in physics? Some physicists argue that the multiverse is inevitable and real, even if unobservable, because it follows directly from well-tested physics. Others argue that an untestable prediction is not physics at all, that science requires the possibility of falsification, and a theory that cannot be falsified in principle is closer to metaphysics than science. This debate is ongoing, and it cuts to the heart of what science is, what counts as evidence, and what it means to understand the universe. There are, interestingly, some potential observational signatures of the multiverse. If our bubble universe collided with another bubble early in its history, a collision between two expanding regions of inflating space, it might have left a detectable imprint on the cosmic microwave background. Researchers have looked for such imprints. So far, none have been found with convincing statistical significance. But the search continues, and future, more sensitive measurements of the cosmic microwave background might reveal something, or they might not. The absence of evidence is not, in this case, evidence of absence. The predicted imprints are subtle, and our instruments may simply not yet be sensitive enough to detect them. What is remarkable is that we are even asking these questions, that we have a coherent, mathematically precise framework, inflation, that makes testable predictions about things we can observe and simultaneously generates predictions about things we cannot, that the equations of physics, developed through centuries of careful observation and reasoning, lead us naturally to the edge of what is knowable and then gesture, almost inevitably, towards something beyond. And that brings us back, in a strange and beautiful way, to the question of motion. Because if the multiverse is real, if there are other bubble universes out there, separated from us by eternally inflating space, then the concept of motion between them is meaningless. There is no path from here to there. There is no speed at which you could travel from one bubble to another, because the space between them is not traversable. It is expanding faster than anything can cross it. Other universes, if they exist, are not distant destinations. They are genuinely, permanently, irreducibly elsewhere, outside the causal structure of our universe, in a way that makes the word elsewhere almost inadequate. Our universe is not just expanding. In the context of eternal inflation, it is a bounded island in an infinite sea of inflating space, a bubble of habitable physics in a cosmos so vast it makes our observable universe, with its 93 billion light-year diameter, look like a single grain of sand on an infinite beach, and you are here, on a planet, in a solar system, in a galaxy, in a supercluster, in a universe, in what may be an infinite multiverse, moving at every scale simultaneously, made of atoms forged in dying stars, asking questions that the universe, as far as we know, is asking only through you. In the next part, we are going to take everything we have covered, all the layers of motion, all the scales of the cosmos, and ask what it actually feels like, not mathematically, not physically, but humanly. What does it mean for a conscious being to be embedded in this kind of universe? And what do the most recent discoveries from the James Webb Space Telescope, from LIGO, from the Event Horizon Telescope, tell us about the universe we are hurtling through, and about how much we still do not understand? Because the universe is not just bigger than we imagined, it is stranger, and the strangeness is not diminishing as we learn more. It is growing. There is a moment that happens to almost everyone who spends enough time thinking seriously about cosmology. A moment where the numbers stop being numbers and start being something else entirely. where the scale of the universe stops feeling like an intellectual exercise and starts feeling like something personal, something almost overwhelming, a kind of vertigo that is not unpleasant, more like standing at the edge of a very high cliff and feeling the pull of the void below, not with fear but with a strange, electric sense of aliveness. If you have not had that moment yet, you might be about to, because we have spent the last several parts of this journey talking about motion and speed and scale in terms of physics, in terms of equations and reference frames and gravitational flows, and all of that is essential. But there is another dimension to this story, the human dimension, the question of what it actually means for a conscious being to exist inside a universe like this one. And that question has been given an entirely new urgency by a series of discoveries over the past few years that have genuinely shaken our understanding of the cosmos in ways that even seasoned astronomers did not fully anticipate. Let's start with the James Webb Space Telescope, because what it has shown us since it began science operations in 2022 is not just beautiful. It is, in several important ways, deeply unsettling. Webb was designed to be the most powerful space telescope ever built. Its primary mirror spans 6.5 meters across, more than 2.5 times the diameter of Hubble's mirror. It observes primarily in infrared light, which allows it to see through the dust clouds that block visible light and to detect the highly redshifted light of extremely distant objects. Galaxies so far away that the light reaching us left them when the universe was only a few 100 million years old. It was placed at a point in space called the second Lagrange point, or L2, roughly 1.5 million kilometers from Earth in the direction away from the Sun, a gravitationally stable location where it can maintain a fixed position relative to Earth while keeping its sensitive instruments permanently shielded from the heat and light of the Sun. The expectations for Webb were enormous. Astronomers anticipated seeing the first galaxies, the earliest structures to form after the Big Bang, as small, irregular, primitive things, chaotic collections of young stars just beginning to coalesce under gravity, simple, messy, the rough drafts of the universe before it had time to develop complexity. What Webb actually found was something quite different. Almost immediately after its first deep field images were released, astronomers began identifying galaxies in the very early universe, existing when the cosmos was only 300 to 500 million years old, that were far more massive, far more structured, and far more developed than any model had predicted. These were not primitive, chaotic proto-galaxies. Some of them were large, well-organized systems containing hundreds of billions of stars. Some showed signs of already having gone through multiple generations of star formation and evolution. Some had stellar populations that, by their chemical composition, implied they were already billions of years old, which, given that the universe itself was only a few 100 million years old at the time, seemed almost paradoxical. The scientific community did not panic. Science does not panic. But there was a genuine, widely acknowledged recognition that something in our models of early galaxy formation was significantly wrong. The standard model of cosmology, called lambda CDM, for lambda cold dark matter, which had been extraordinarily successful at explaining the large-scale structure of the universe, was apparently underestimating how quickly galaxies could form and grow in the early universe. The early universe was apparently a far more efficient factory for building massive structures than anyone had calculated. Now, this does not mean the Big Bang is wrong. It does not mean the age of the universe is wrong. It does not mean cosmology is in crisis in any fundamental sense. What it means is that our models of how matter clumped together under gravity in the first few 100 million years, models that depend critically on the behavior of dark matter, on the rate of star formation, on the feedback mechanisms that regulate how quickly galaxies grow, are incomplete. Some ingredient is missing, some process is happening faster or more efficiently than our simulations account for. Finding out what that ingredient is, that is where cosmology is right now, on the edge of something, accumulating observations that do not quite fit the existing framework, and knowing that the framework will need to be extended, revised, or perhaps in some areas replaced. This is not a crisis. This is science working exactly as it should. Anomalies are the most valuable things in science, anomalies of where the new physics hides, and Webb has delivered anomaly after anomaly. Another striking example involves what are called little red dots, compact, extremely bright objects observed in the early universe that appear to be neither typical galaxies nor typical quasars, but something in between, or perhaps something entirely new. They are too bright, too compact, and too numerous to fit comfortably into any existing category. Researchers are still actively debating what they are, what they tell us about early black hole formation, and whether they require new physics to explain. The debate is ongoing, and it is genuinely exciting, the kind of scientific argument that ends up being cited decades later as the moment when something fundamental was discovered. Then there is what cosmologists are calling the Hubble tension. This one has been building for several years, and it is serious enough that it was already causing significant debate before Webb launched. Here is the core of it. There are two primary ways to measure the current expansion rate of the universe. A number called the Hubble constant, usually written as h0. The first method uses the cosmic microwave background. By analyzing the detailed pattern of temperature fluctuations in this ancient radiation, essentially reading the acoustic ripples that were frozen into it when the universe was about 380,000 years old. Cosmologists can build a precise model of the early universe and extrapolate forward to predict what the expansion rate should be today. The Planck satellite, which mapped the cosmic microwave background with extraordinary precision between 2009 and 2013, produced a value of approximately 67 kilometers per second per megaparsec for the Hubble constant. A megaparsec is about 3.3 million light-years. The second method measures the expansion rate directly, using objects in the relatively nearby universe. Astronomers use a chain of distance measurements, called the cosmic distance ladder, starting with nearby stars, whose distances can be measured geometrically, then using those to calibrate the brightness of certain types of variable stars called Cepheids, then using the Cepheids to calibrate the brightness of type Ia supernovae, and finally using the supernovae to measure distances and recession velocities across cosmic scales. This method, refined over decades by groups including the SH0ES team led by Adam Rias, consistently produces a higher value, approximately 73 kilometers per second per megaparsec, 67 versus 73. That gap might not sound dramatic, but in cosmological terms it is enormous. The measurements are precise enough, the error bars are small enough that the two values simply should not disagree by this much if the standard model is correct. The probability that the disagreement is a statistical fluke is extremely low. Both methods have been checked, rechecked, and refined extensively. The tension has not gone away. If anything, as measurements have become more precise, it has become more significant. One hope was that Webb would resolve the tension by revealing systematic errors in the Cepheid-based distance measurements. Perhaps the Cepheids in crowded star fields were being contaminated by the light of nearby stars, artificially affecting their measured brightness. Webb's infrared vision and extraordinary resolution are perfectly suited to testing this. Early results from Webb showed that the Cepheid measurements are actually more reliable than some had feared. The contamination is smaller than the skeptics hoped. the tension did not go away, which means one of a few things. Either there is a systematic error somewhere that has not yet been identified in one or both measurement methods, or the standard cosmological model is missing something, a new form of energy in the early universe, a different behavior of dark energy over time, a modification to general relativity at cosmological scales. Something that changes the expansion history of the universe in a way that reconciles the two measurements. Whatever the resolution turns out to be, it will teach us something fundamental about the universe. A discrepancy this persistent and this significant does not come from nothing. It is pointing at something real, and finding that something, that is one of the central projects of observational cosmology right now. While all of this has been unfolding in the optical and infrared, an entirely different kind of astronomy has been producing its own extraordinary revelations. We mentioned gravitational waves earlier, but the story of what LIGO and Virgo have revealed about the universe deserves more than a brief mention. When LIGO detected its first gravitational wave signal in September of 2015, it confirmed a prediction that Einstein had made 99 years earlier. But the confirmation was just the beginning. What followed was an entirely new observational window onto the universe, and the view through that window has been full of surprises. One of the most significant came in August of 2017, when LIGO and Virgo detected gravitational waves from the merger of two neutron stars. Unlike black hole mergers, which produce no light, neutron star mergers are spectacularly bright across the electromagnetic spectrum. Within seconds of the gravitational wave detection, gamma-ray observatories detected a short gamma-ray burst from the same location. Over the following days and weeks, telescopes around the world trained their instruments on the source, a galaxy called NGC 4993, about 130 million light-years away, and observed what is called a kilonova, an explosion so energetic it produces and ejects elements heavier than iron, gold, platinum, uranium, and dozens of others. In quantities that dwarf anything a single star could produce, this observation was transformative for multiple reasons. It confirmed that short gamma-ray bursts, some of the most energetic explosions in the universe, are caused by neutron star mergers. It confirmed that heavy elements like gold are produced primarily in these mergers, not in supernovae as had long been assumed. And it demonstrated the extraordinary power of multi-messenger astronomy. Combining gravitational wave detection with electromagnetic observations to build a complete picture of a cosmic event that neither method could fully describe alone. The gold in any jewelry you own, the platinum in catalytic converters, the uranium in nuclear reactors, these elements were forged in the collision of neutron stars, in explosions like the one LIGO detected in 2017. They drifted through space as gas and dust for billions of years before being swept up in the cloud that eventually collapsed to form our solar system. They have been inside Earth for 4.5 billion years, and inside living things for as long as life has existed. They are inside you right now. You are not just made of stardust in the poetic general sense. You are made of the specific debris of specific catastrophic events, stellar explosions, neutron star collisions that happened in specific places at specific times before our sun was born. The iron in your blood was forged in a supernova. The calcium in your bones was made in a dying star. The oxygen you breathe with every breath was produced by generations of stars that lived and died over billions of years. You are a temporary assembly of some of the universe's most widely traveled atoms, forged in stellar furnaces, scattered by explosions, drawn together by gravity, organized by chemistry into something that can sit here and contemplate its own cosmic origins. That is not a metaphor. That is chemistry. That is nuclear physics. That is the story the periodic table tells when you read it carefully enough. And here is what makes that even more staggering. The atoms in your body are almost entirely empty space. A hydrogen atom consists of a proton and an electron, with the electron occupying a fuzzy quantum cloud around the nucleus. If you scaled the proton up to the size of a marble, the electron cloud would extend to roughly 1 kilometer away. Everything in between is empty. You are made of atoms, and atoms are made almost entirely of nothing, of vast quantum emptiness punctuated by tiny concentrations of matter so small they defy imagination. When LIGO measures a gravitational wave, it is measuring the stretching and compressing of space-time by distances smaller than 1/10,000th the diameter of a proton, and yet the instrument detects it. And yet it is real. The universe operates at scales of precision so far beyond ordinary human experience that every measurement feels like an act of almost miraculous ingenuity. The Event Horizon Telescope has added yet another dimension to this picture. In April of 2019, a global network of radio telescopes spread across multiple continents, functioning as a single Earth-sized dish through a technique called Very Long Baseline Interferometry, produced the first direct image of a black hole, specifically the supermassive black hole at the center of the galaxy M87, located about 55 million light-years away. The image showed a bright ring of glowing plasma surrounding a dark central region, the shadow of the black hole, where gravity is so extreme that even light cannot escape. Then, in May of 2022, the Event Horizon Telescope collaboration released an image even closer to home, the first image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. Sagittarius A star is about 4 million times the mass of our Sun, and it sits roughly 26,000 light-years from Earth. The image confirmed what had been inferred from decades of stellar orbit measurements, that there is indeed a supermassive black hole at the galactic center, and it looks strikingly similar to the one in M87, despite being more than 1,000 times less massive. These images matter not just as scientific achievements, but as perspective-giving moments, because Sagittarius A star, this object whose image we have now captured, is the gravitational anchor around which our entire solar system orbits. Every galactic year, every 225 to 250 million years, we complete one orbit around this thing. It has been there at the center of our galaxy for billions of years. It has been the focal point of our solar system's endless journey through the Milky Way for as long as our Sun has existed. And now we have a picture of it. There is something almost intimate about that. Something that collapses the enormous distance between 26,000 light-years away and the screen you are watching this on. We looked toward the center of our galaxy, and we saw the thing that has been guiding our path through the cosmos for 4.5 billion years. We took its portrait. Now think about all the layers of motion we have described, all the spinning and orbiting and hurtling and flowing, and consider that every single one of those motions has been happening continuously for billions of years. Earth has completed more than 4 billion rotations. It has completed more than 4 billion orbits of the Sun. Our solar system has completed roughly 20 orbits of the galactic center. The Milky Way has been flowing toward the Great Attractor for as long as large-scale structure has existed. All of this motion, relentless, continuous, unimaginably vast, and throughout all of it, not once has Earth paused. Not once has the solar system stopped. Not once has the Milky Way hesitated in its journey. And throughout most of that time, the universe had no one to notice, no consciousness to observe it, no mind to measure it or be awed by it. The stars were born and burned and died in complete silence, not the silence of sound, but the silence of meaning. No one was there to find it beautiful, to feel the vertigo of the scale, to construct the equations that describe the motion, to build the telescopes that measure it. And then, In the last few 100,000 years, a cosmic eye blink, something changed. On a small rocky planet orbiting an unremarkable star in the outer spiral arm of an average galaxy, matter organized itself into a form that could look up and wonder, that could feel awe, that could ask questions and pursue answers and build instruments of extraordinary delicacy to probe the nature of reality. That could watch a video about the speed of the universe and feel for a moment the full staggering weight of what it means to be here. That is you. That is what you are, not a passenger in the universe, not an observer standing outside it looking in. You are part of it. You are the universe observing itself, a temporary local increase in complexity and awareness, embedded in a cosmos that is 440,000 times older than your species, moving through space at speeds your nervous system was never designed to perceive, made of atoms that have been on journeys spanning billions of years and billions of light years before they briefly, temporarily came together to form you. And in the next part of this journey, we are going to take that sense of connection, that feeling of being genuinely embedded in the cosmos, and push it further. Because there are aspects of our motion through the universe that are not just philosophically interesting. They have direct, measurable consequences for life on Earth, for the climate, for the geology, for the biological history of this planet. The way we move through the galaxy is not a background fact. It is a driver of events. It shapes the conditions that made your existence possible. And understanding those connections reveals a universe that is not indifferent to the existence of life, not because it cares, but because it is structured in ways that make complexity, chemistry, and consciousness almost inevitable. The story of how our motion through the cosmos connects to the story of life on Earth. That is where we are headed, and it is stranger and more beautiful than you might expect. Here is something that almost never gets talked about in the mainstream conversation about space and astronomy. Something that sits at the intersection of astrophysics, geology, biology, and the history of life on Earth in a way that should be far more widely known than it is. The motion of our solar system through the galaxy is not just an abstract fact about our cosmic address. It has consequences. Real, measurable, deeply significant consequences for what has happened on this planet over billions of years. And when you start connecting those consequences to the history of life, to the great extinctions, to the ice ages, to the rise and fall of dominant species, the universe stops feeling like a backdrop and starts feeling like an active participant in the story of Earth. Let's start with something called the Galactic Plane. The Milky Way is a disc-shaped galaxy, and like most disk galaxies, the bulk of its mass, its stars, its gas clouds, its dust, its dark matter, is concentrated in a relatively thin plane. Our solar system orbits within this disk, but it does not travel in a perfectly flat circle. It bobs. It oscillates up and down through the galactic plane like a horse on a carousel, crossing above and below the midplane of the galaxy on a rhythm that takes roughly 60 to 70 million years to complete one full oscillation. Up through the plane, above it, then back down, through it again, below it, and back up, over and over, continuously for the entire history of our solar system. This oscillation matters because the density of matter in the galaxy is not uniform. Near the galactic midplane, where the concentration of stars and gas clouds is highest, the gravitational environment is more complex and more intense. The outer Oort cloud, a vast, spherical shell of icy bodies surrounding our solar system at distances of up to 100,000 astronomical units from the Sun, is sensitive to gravitational perturbations. When the solar system passes through regions of higher stellar density near the galactic plane, the gravitational influence of passing stars and molecular clouds can disturb the Oort cloud, sending showers of comets plunging into the inner solar system. And comet showers historically have not been good news for life on Earth. The idea that our galactic position influences comet flux, and therefore the rate of major impact events on Earth, was developed and refined by researchers including Michael Rampino and Richard Stothers in the 1980s, and has been explored extensively since then. The hypothesis suggests that the roughly 60 to 65 million year periodicity in some extinction events in the fossil record might be connected to the solar system's oscillation through the galactic plane. The numbers are not a perfect match. The geological and paleontological record is noisy, and the galactic oscillation period is not precisely constrained, but the correlation is intriguing enough to have remained an active area of research for decades. The most famous extinction event in Earth's history, the end Cretaceous extinction 66 million years ago, which wiped out the non-avian dinosaurs and roughly 75% of all species on Earth, was caused by an asteroid impact, confirmed by overwhelming geological evidence, including the discovery of the Chicxulub crater in Mexico and the global layer of iridium-rich sediment that marks the boundary between the Cretaceous and Paleogene periods. But other extinction events, the end Permian extinction 252 million years ago, which was the most devastating in Earth's history, killing perhaps 96% of all marine species and 70% of terrestrial vertebrate species, may have had more complex, multi-causal origins that could include voluminous volcanic activity, climate shifts, and potentially contributions from the galactic environment. This is not settled science. The connections between galactic dynamics and Earth's extinction record are suggestive rather than proven. But the framework, the idea that Earth's biological history is not entirely self-contained, that it is influenced by our position and motion within the galaxy, is legitimate, taken seriously by researchers, and deeply fascinating as a way of thinking about the relationship between cosmic and terrestrial history. There is another galactic structure that our solar system interacts with periodically, and its effects are more directly observable. The Milky Way's spiral arms are not solid structures, they are more like density waves, regions of compressed gas and stars that rotate around the galactic center at a different rate than the stars themselves. Our solar system moves in and out of spiral arm regions as it orbits the galaxy, spending time in the denser, more active regions between the arms and occasionally crossing through an arm itself. Spiral arms are where star formation is most active. They are dense with molecular gas clouds, the raw material for new stars, and with the young massive hot stars that form quickly, burn brightly, and die violently. When our solar system passes through or near a spiral arm, it enters a region of the galaxy that is more dangerous, in a sense, more populated with the kind of massive stars that explode as supernovae, bathing their surroundings in intense radiation, cosmic rays, and the shock waves of their deaths. Supernovae at close enough range, within perhaps 30 light-years, could be genuinely catastrophic for life on Earth. The radiation and cosmic rays from a nearby supernova could strip away parts of the ozone layer, exposing the surface to intense ultraviolet radiation from the sun. There is evidence in the geological record, notably in deposits of radioactive isotopes like iron-60, which is produced in supernova explosions and is not naturally abundant on Earth, of nearby supernova events in the relatively recent geological past. A concentration of iron-60 in ocean sediments dating to roughly 2 to 3 million years ago suggests that one or more supernovae exploded within perhaps a few hundred light-years of Earth during that period. 2 to 3 million years ago is, incidentally, roughly when our genus, Homo, was beginning to emerge in Africa. Whether there is any connection between nearby supernova activity and the evolutionary pressures that shaped early human ancestors is speculative, but the timing is noted, and researchers have considered the possibility that increased cosmic ray flux from nearby supernovae could have influenced climate, and therefore the ecological environment in which our ancestors evolved. This is the universe as an active participant in Earth's history, not a passive backdrop, not an indifferent void. A dynamic environment whose properties, the density of nearby stars, the frequency of energetic events, the gravitational influences of passing clouds and stellar clusters, vary depending on where in the galaxy we happen to be at any given moment. And where we are depends entirely on our motion. The journey matters, the path matters. The fact that we orbit the galactic center at 828,000 kilometers per hour on a specific trajectory that takes us through specific regions of the galaxy at specific times in geological history, that is not a trivial detail. It is part of the story of why Earth has the history it does. There is also a longer-term perspective worth considering here. Our solar system is currently located in what astronomers call the Orion Arm, or sometimes the Local Arm, a relatively minor spur between two of the major spiral arms of the Milky Way, the Sagittarius Arm on one side and the Perseus Arm on the other. This is, in a very specific sense, a quiet neighborhood. We are not in the thick of a major spiral arm, with all the energetic activity and dense stellar populations that come with it. We are in a calmer, less crowded region, still within the galactic disk, still moving through a complex environment, but not in the most turbulent part of it. Some researchers have argued that this location is not a coincidence, or rather, that it may be one of many factors that have allowed complex life to develop and survive on Earth for hundreds of millions of years without being sterilized by a nearby catastrophic event. This is part of a broader concept called the Galactic Habitable Zone, the idea that, just as planets need to be in a certain range of distances from their star to support liquid water, solar systems need to be in a certain range of positions within their galaxy to have conditions suitable for complex life. Too close to the galactic center and the radiation environment is too intense, the stellar density too high, the frequency of gravitational perturbations too disruptive, too far from the center, and the abundance of heavy elements, the atoms needed to build rocky planets and the chemistry of life, drops too low. The galactic habitable zone is thought to lie in a ring-shaped region at intermediate galactic radii, and our solar system sits comfortably within it. We are, in other words, in a good spot, not just in the solar system, on a planet at the right distance from the Sun, with the right chemistry, with a large moon that stabilizes our axial tilt, and a giant planet in the outer solar system that deflects many incoming comets, but also in the galaxy, in a quiet spur at a favorable galactic radius, at a moment in galactic history when conditions are relatively stable. The improbability of all these factors aligning is part of what makes Earth and life and consciousness feel like something almost extraordinary, even within a universe that contains hundreds of billions of galaxies. Now, here is where the perspective shifts in a way that I find genuinely moving. We have been talking about our motion through the cosmos largely in terms of speed and scale and physical consequence. But there is a more intimate dimension to this story, one that does not involve telescopes or equations, but that is just as real and just as scientifically grounded. Every atom in your body is participating in all of this motion, every single one. The carbon in your DNA, the iron in your hemoglobin, the calcium crystallized in your bones, the hydrogen and oxygen in every molecule of water in every cell, all of it is spinning with the Earth, orbiting the Sun, sweeping around the galactic center, flowing toward the great attractor, embedded in the expanding universe. Your atoms are not observers of this motion. They are participants. They are being carried along on the same journey as every star in the Milky Way, every galaxy in Laniakea, every structure in the cosmic web, and those atoms have a history that dwarfs the history of life of Earth, of the solar system. The carbon in your body was forged in the core of a star that lived for millions or billions of years, burning hydrogen into helium and helium into carbon and oxygen and heavier elements until its fuel was exhausted and it expelled its outer layers into space in a stellar wind or a dramatic explosion. That carbon drifted through interstellar space for millions of years, part of a vast, cold molecular cloud, until gravity slowly drew the cloud together, collapsing it into a disk of gas and dust, at the center of which our sun ignited roughly 4.5 billion years ago. The leftover material in that disk clumped together to form the planets, and some of that carbon ended up on Earth, dissolved into the early oceans, incorporated into the first simple molecules, and eventually, through a chain of chemical events that we still do not fully understand, into the first living cells. From there, over billions of years, through evolution and adaptation and extinction and diversification, that carbon passed through countless organisms. It was in single-celled bacteria in the Archean oceans. It was in the first multicellular animals in the Cambrian seas. It was in ferns and insects and fish and reptiles and mammals across hundreds of millions of years of biological history. And now it is in you, arranged, temporarily, in the specific configuration of molecules and cells and tissues and organs that constitutes a living, thinking, feeling human being. Your carbon has been on a journey spanning billions of years and billions of light years. It has been inside stars, inside molecular clouds, inside ancient seas, inside organisms that went extinct long before anything resembling a human existed. And now it is here, inside you, while you move through the universe at over 1 million kilometers per hour. That is not poetry. That is the actual history of the matter that makes you up. And knowing it, really knowing it, feeling the weight of it, changes something about how you see yourself in relation to the cosmos. You are not separate from the universe, looking at it from the outside. You are part of it, looking at itself from the inside. Every observation you make, every thought you think, every feeling you have, these are events happening inside the universe, not outside it. You are the universe being aware of itself, temporarily, in one small corner of one spiral arm of one galaxy among hundreds of billions, and the motion, all that staggering, layered, relentless motion, that is not something happening to you. It is something you are part of. You are not a passenger. You are not cargo. You are an expression of the same physics, the same forces, the same underlying reality that drives every galaxy, every star, every subatomic particle, the spin of Earth, the orbit of the solar system, the flow of the Milky Way through Laniakea. These are not separate from you. They are you at a different scale. The universe does not move and then carry you along. It moves, and you are part of how it moves. There is a concept in philosophy called the overview effect, a term coined by writer Frank White to describe the cognitive shift experienced by astronauts when they see Earth from space for the first time. Every astronaut who has described the experience uses similar language, the sense of Earth's fragility, the absence of borders, the recognition that from space, all the divisions that seem so important on the surface, national, cultural, ideological, are invisible. There is just this one small, luminous world hanging in the dark. But there is a deeper version of that effect that does not require going to space. It requires only understanding, truly understanding where you are and how you are moving. The overview effect of cosmology, the recognition that you are not on a planet orbiting a star. You are on a planet orbiting a star in a solar system, orbiting a galaxy in a supercluster flowing through a cosmic web inside an expanding universe that may be just one of an infinite number of universes. And that all of this, all of it, is in motion, has always been in motion, and will continue to be in motion long after every star that currently shines has burned out and faded to darkness. That recognition does not make you feel small. Or rather, it does, but not in a diminishing way. It makes you feel small, the way standing at the edge of the ocean makes you feel small. Not crushed, not insignificant, but connected, part of something vast and old and beautiful and strange. Something that was here long before you arrived and will be here long after you are gone, but that is, right now, in this moment, being experienced through you. And that is something the universe has not always been able to do. For most of its 13.8 billion years, the cosmos has existed without anything in it capable of appreciating what it is. The galaxies formed and collided and merged in complete experiential darkness. The stars burned and exploded without witness. The cosmic web assembled itself over billions of years without a single mind to notice. And then, in the last fraction of a percent of cosmic time, on one small planet around one ordinary star, something happened. The universe developed the capacity to know itself, to measure itself, to be astonished by itself. You are that capacity, right now, in this moment. Whatever else you are, whatever else your life contains. You are also the universe's way of being amazed at the universe. If you are still watching, then you're exactly the person I make these videos for. Don't forget to give the video a thumbs up and subscribe. You will be part of a community that explores the cosmos together. Where does it all end up? That is the question sitting underneath everything we have talked about, because motion implies direction. Direction implies destination. And if you follow the trajectory of the universe far enough into the future, if you trace the path of all this motion across timescales that dwarf everything we have discussed so far, you arrive at a set of possible endings that are, depending on your perspective, either profoundly beautiful or profoundly sobering, or, if you are willing to sit with the full weight of them, somehow both at the same time. Let's start with where we are going in the relatively near term. Cosmically speaking, of course, because in cosmic time, even a billion years is a short chapter. The Milky Way and the Andromeda Galaxy, our nearest large galactic neighbor, sitting roughly 2.5 million light-years away, are moving toward each other. This is not a recent discovery. Astronomers have known for some time that Andromeda is approaching us, its light blue-shifted rather than red-shifted, indicating motion toward us rather than away. But for a long time, there was uncertainty about whether the two galaxies would actually collide or simply pass by each other at a safe distance. That uncertainty was resolved by data from the Hubble Space Telescope and later refined by the European Space Agency's Gaia mission, which has been mapping the positions and motions of over 1 billion stars in the Milky Way with extraordinary precision. The conclusion is clear. In approximately 4.5 billion years, the Milky Way and Andromeda will collide, not in the way that word might suggest, not a violent crash of stars smashing into each other, but a slow, gravitationally choreographed merger that will unfold over hundreds of millions of years. Because galaxies are mostly empty space, the odds of any two individual stars actually colliding during the merger are extremely low. What will happen instead is that the gravitational interaction will distort both galaxies profoundly, pulling long tidal streams of stars out into intergalactic space, triggering massive bursts of star formation as gas clouds are compressed by the collision, and gradually, over several passes and billions of years, merging the two spiral galaxies into a single, larger elliptical galaxy. Astronomers have already given this future galaxy a name, Milkomeda, or sometimes Milkdromeda, and simulations of the merger, refined over years using increasingly powerful computers and increasingly precise measurements of both galaxies' motions, paint a picture of extraordinary cosmic drama. The night sky during the merger, billions of years from now, assuming anything is around to observe it, would look nothing like the sky we see today. Andromeda, currently invisible to the naked eye for most people, would grow larger and larger over millions of years. eventually becoming a vast, luminous structure spanning much of the sky. As the two galaxies begin to interpenetrate, the stellar density around any planet in either galaxy would increase dramatically. Star formation would surge. The sky would be far more populated with bright, young, massive stars than it is today. Our own Sun will not survive to see the merger completed. In approximately 5 billion years, slightly before the collision, the Sun will exhaust the hydrogen fuel in its core and begin the final stages of its life. It will swell into a red giant, expanding to perhaps 100 to 200 times its current diameter, engulfing Mercury and Venus, and possibly Earth as well. Even if Earth's orbit shifts outward enough to avoid being physically swallowed, a possibility that depends on models of mass loss during the red giant phase, the surface of the planet will be sterilized long before the Sun reaches its maximum size. The oceans will boil away. The atmosphere will be stripped off. Whatever life remains on Earth at that point will have long since needed to find somewhere else to be. This is not a cause for despair. 5 billion years is an almost incomprehensible span of time. Our species has existed for a few 100,000 years. Recorded human civilization is only a few thousand years old. In 5 billion years, if humanity or its descendants still exist, they will be something so profoundly different from what we are today that the question of what happens to Earth is almost meaninglessly abstract. The beings who might need to worry about the Sun's death are not us. They are something we cannot currently imagine, descended from us across a chain of transformation so long and so deep it makes the distance between us and our single-celled ancestors seem modest. But let's follow the thread further, past the Sun's death, past the Milky Way-Andromeda merger, into the truly deep future where the timescales become so vast that our ordinary intuitions about time completely break down. After the merger of the Milky Way and Andromeda, after Milkomeda has settled into a single elliptical galaxy, the local group will continue to evolve. The smaller galaxies orbiting the Milky Way and Andromeda, the Magellanic Clouds, the Triangulum Galaxy, and dozens of smaller dwarf galaxies will also eventually be absorbed either into Milkomeda or into each other. Over tens of billions of years, the local group will slowly consolidate into a single large galaxy as all its members merge under their mutual gravity. But the rest of the universe will be pulling away. Because of dark energy, the expansion of space will continue to accelerate, carrying all the galaxy clusters and superclusters beyond our local group further and further away. The Virgo cluster, the heart of the local supercluster, containing thousands of galaxies, is gravitationally bound to our neighborhood, and current models suggest that our local group and the Virgo cluster will eventually be drawn together into a larger structure. But beyond that, the accelerating expansion will make everything else increasingly unreachable. Galaxy after galaxy, cluster after cluster, will cross the Hubble horizon, moving away from us faster than light, their signals forever unable to reach us. In roughly 100 billion years, about 7 times the current age of the universe, the observable universe as seen from whatever remains of our galaxy will contain only the merged local group and perhaps a handful of the most gravitationally bound nearby structures. Everything else will have disappeared beyond the cosmic horizon. The universe will appear to consist of a single enormous galaxy surrounded by what looks like an empty void. Any observer at that point, without a record of what came before, would have no way of knowing that hundreds of billions of other galaxies once filled the observable sky. This is one of the most poignant facts in all of cosmology. We live in a privileged moment. The cosmic web is still visible. The billions of galaxies are still there, still detectable, still mappable. The evidence of the universe's true scale and complexity is still accessible to us. But it is a temporary window. The universe is gradually hiding its own history. erasing the evidence of its grandeur as the expansion carries it beyond reach. In a sense, the universe is becoming less knowable over time, not because it is becoming simpler, but because the information about its complexity is being swept away by the very expansion that created the conditions for complexity in the first place. Now push further, much further, into timescales that make 100 billion years look like an afternoon in roughly 10 to the power of 14 years, 100 trillion years, about 10,000 times the current age of the universe. The last stars will burn out. Star formation, which depends on the availability of cold gas clouds that can collapse under gravity, will gradually decline as the gas in galaxies is consumed. New stars will form more and more slowly, and the stars that remain will live out their lives without replacement. The most massive stars die first, within millions of years. Stars like our Sun live for roughly 10 billion years. The smallest, coolest red dwarf stars, the most numerous type in the galaxy, burn so slowly and so efficiently that they can live for trillions of years. But even they will eventually exhaust their fuel. When the last red dwarf burns out, the universe will enter what cosmologists call the degenerate era. The galaxy, whatever Milky has become by then, will be populated not by shining stars but by the cold remnants of stars, white dwarfs, the cooling cores of sun-like stars drifting in the dark, neutron stars, the ultra-dense remnants of massive stars that exploded as supernovae, spinning slowly down over trillions of years, black holes, the collapsed remnants of the most massive stars, orbiting each other in the cold darkness. For an almost unimaginably long time, these stellar remnants will continue to interact gravitationally. Occasionally, two white dwarfs will collide and briefly ignite in a thermonuclear explosion. Occasionally, a stellar remnant will be gravitationally scattered out of the galaxy entirely, ejected into intergalactic space, slowly, over timescales of roughly 10 to the power of 19 to 10 to the power of 20 years, numbers so large that writing them out in full would take more space than this entire script. Gravitational interactions will cause the stellar remnants to spiral inward toward the central black hole, or be flung outward into the void. The galaxy will gradually dissolve, and the black holes themselves, even they are not permanent. In 1974, the physicist Stephen Hawking made one of the most surprising theoretical predictions in the history of physics. Using a combination of quantum mechanics and general relativity, the two frameworks that are otherwise incompatible, he showed that black holes are not perfectly black. They emit radiation, very slowly, very faintly, but continuously. This radiation, now called Hawking radiation, arises from quantum effects near the event horizon of the black hole, and it causes the black hole to very gradually lose mass over time. Given long enough, any black hole will eventually evaporate completely, radiating away its entire mass as a faint hiss of thermal radiation. How long does this take? For a stellar mass black hole, one with perhaps 10 times the mass of the Sun, the evaporation time is roughly 10 to the power of 74 years. For a supermassive black hole like Sagittarius A star, with 4 million solar masses, the evaporation time is closer to 10 to the power of 100 years. These are numbers that have no human analogy. The current age of the universe, 13.8 billion years, is utterly negligible compared to these timescales. The age of the universe is to the evaporation time of a supermassive black hole what a single second is to the age of the universe, and then some. But given enough time, and the future of the universe apparently has time in effectively unlimited supply, even the supermassive black holes will evaporate. And when the last black hole is gone, the universe will enter what is sometimes called the dark era, a state of maximum entropy, maximum disorder, in which no further useful energy extraction is possible. The universe will be filled with a faint, cold, uniform bath of photons and other particles, all at nearly the same temperature, all spreading out through an ever-expanding space. No gradients, no structures, no sources of energy, no possibility of anything happening that could be called an event in any meaningful sense. This is the ultimate destination of all the motion we have been describing. The spinning, the orbiting, the hurtling, the flowing, all of it leads eventually to stillness. Not the stillness of rest, but the stillness of thermal death, the heat death of the universe, maximum entropy, the final state. This scenario, called the Big Freeze, or heat death, is the most likely long-term fate of the universe given current cosmological observations. It is the consequence of dark energy remaining constant, of the second law of thermodynamics operating without exception over infinite time, of entropy always increasing until it reaches its maximum value and nothing further can change. But, and this is important, there are alternatives, and not all of them are bleaker than heat death. Some are stranger. If dark energy is not a constant but grows stronger over time, if the equation of state of dark energy evolves in a particular way, the universe could end in the big rip we discussed earlier, the expansion accelerating without limit until it tears apart every structure, every atom, every particle, a violent end rather than a cold, quiet one. If dark energy weakens over time, if it eventually reverses, the expansion of the universe could slow, stop, and reverse. Gravity would then become dominant, pulling everything back together. The universe would contract, growing hotter and denser as it collapsed, until everything reconverged in an event called the Big Crunch. Essentially the reverse of the Big Bang, a final singularity in which all of space, time, matter, and energy converge back into a state of infinite density. Some theoretical frameworks suggest that the Big Crunch might be followed by another Big Bang, a cyclic universe, bouncing between expansion and contraction over and over, with no ultimate beginning and no ultimate end. Then there is an idea called vacuum decay, or false vacuum decay, which is arguably the most unsettling of all possible cosmic fates. The quantum vacuum, the lowest energy state of empty space, might not actually be the true lowest energy state. It might be a metastable state, a local minimum in an energy landscape rather than the global minimum. If that is the case, quantum mechanics allows for the possibility of a bubble of lower energy vacuum nucleating somewhere in space, spontaneously appearing the way radioactive nuclei spontaneously decay. And that bubble, once it appears, would expand outward at the speed of light, converting the quantum vacuum around it to its new, lower energy state. The laws of physics inside the bubble would be different from the laws outside it. Different fundamental constants, different rules, different particle masses, different forces. Everything inside the bubble would be instantly and completely destroyed, not in any explosive or violent sense that implies suffering, but in the sense that the underlying physics that allows atoms, molecules, chemistry, and biology to exist would simply cease to apply. The bubble wall would arrive without any warning. You cannot see something traveling toward you at the speed of light before it arrives. And in the moment of its arrival, everything would end. Not with a bang, not with a whimper, just differently. The good news, if it can be called that, is that we have no evidence that the universe's vacuum is unstable. The current best measurements of the Higgs boson mass, made at the Large Hadron Collider at CERN, place the universe in what physicists call a metastable state, possibly unstable, but with a decay time that is almost certainly far longer than the current age of the universe, and possibly far longer than any of the other cosmic timescales we have discussed. It is a theoretical possibility, not an imminent threat, but it is worth knowing about because it represents a genuinely different kind of ending, one that does not unfold gradually over trillions of years, but could in principle happen at any moment, anywhere in the universe, without warning. Now, after all of that, After following the trajectory of the universe from its violent inflationary birth through the long, slow, stately evolution of galaxies and stars and life, all the way to the cold darkness of heat death, or the violence of the Big Rip, or the cyclic drama of the Big Crunch, it is worth pausing, taking a breath, and asking what any of this means for how we think about the motion we started with. Because we started with a simple question: how fast are you moving through the universe? And we followed that question through layer after layer of motion: the spin, the orbit, the galactic rotation, the cosmic flow, the expansion of space, until we arrived here at the end of time, contemplating the ultimate fate of all that movement. And what the long view reveals is something subtle but important. Motion, in the context of the universe's full history, is not just about speed. It is about direction. And the direction of the universe, the arrow of time, the increase of entropy, the expansion of space, the gradual dispersal of all the energy and structure that the Big Bang created, points in one direction only: forward, always forward, towards states of greater disorder, greater dispersal, greater uniformity. Everything that exists, every star, every galaxy, every living thing, is a temporary island of order in a universe trending toward disorder. The fact that we exist at all, that the universe has produced regions of such extraordinary complexity and organization as a planet teeming with life, is a consequence of the initial conditions of the Big Bang, the extraordinarily low entropy state from which everything began. The Big Bang did not just create matter and energy. It created a universe with an enormous amount of available order, a universe far from equilibrium, and the history of the cosmos is, in one sense, the story of that order being gradually spent, transformed, dispersed. Life is one of the most remarkable ways the universe has found to spend that order. Living things take in energy, use it to build and maintain extraordinarily complex structures, and release it as heat. We are, thermodynamically speaking, highly efficient processors of entropy, and consciousness, the ability to experience, to think, to feel, to wonder, is perhaps the most complex information processing system the universe has produced. The brain you are using to understand these words contains roughly 100 billion neurons, connected by approximately 100 trillion synapses, firing in patterns of extraordinary subtlety and richness. It is, by any reasonable measure, the most complex structure we have ever found in the observable universe, and that structure is moving through the cosmos at over 1 million kilometers per hour, right now, made of atoms from dead stars, sitting on a planet that has been on a continuous journey through the galaxy for 4.5 billion years, embedded in a universe that began in an explosion of space 13.8 billion years ago and will end in one way or another, in a future so distant it makes the present moment feel like the very first instant of time. You are here, you are aware, you are moving, and you are, in this moment, the universe's most intricate and improbable way of knowing that all of this is true. Let's come back down to Earth for a moment, literally, because after everything we have covered, the billions of light years, the trillions of years, the heat death of the universe, the evaporation of black holes, there is something important that gets lost if you stay too long at the cosmic scale. Something that the science of our motion through the universe actually has to say about the texture of ordinary human life, about the way you move through your days, about the way you relate to the people around you, about what it means to be alive on this particular planet at this particular moment in cosmic history. And the starting point for that conversation is something deceptively simple: the fact that you have never been in the same place twice. Think about that carefully. Every moment you exist, you are at a unique position in the universe that has never been occupied before and will never be occupied again. The Earth is spinning, the solar system is orbiting the galaxy is moving through Laniakea, The entire cosmic web is being stretched by the expansion of space. The combination of all these motions means that every second you are somewhere new, not just in the local, everyday sense of moving from room to room, but in the absolute sense. The coordinates of your position in the universe, accounting for all the layers of motion we have described, change continuously and irreversibly. You are always in new territory, always. There is no going back to a previous position. There is no returning to where you were. The universe does not allow it. The geometry of space-time, the expansion of the cosmos, the irreversibility of time, all of these conspire to make every moment genuinely, literally unrepeatable. The atoms that make up your body are at a unique location in the universe right now that they have never occupied before and will never occupy again. Every breath you take happens at a different point in the cosmos than the one before it. This is not mysticism, it is physics. And what it suggests, if you let it sink in, is that the present moment has a kind of cosmic uniqueness that goes far beyond anything we usually attribute to it. We talk about living in the present as a philosophical or psychological practice, being mindful, being here, paying attention to what is happening now rather than what happened then or what might happen later. But the physics of our motion through the universe gives that practice a literal grounding. The present moment is not just psychologically unique, it is cosmically unique. It is the only time you will ever be exactly here. Now, there is a tension in this that is worth sitting with, because the same physics that makes every moment unique also makes every moment transient. The universe is always in motion, always changing, always moving towards states of greater entropy. Nothing lasts. Stars burn out, galaxies dissolve, even the most durable structures in the cosmos. Black holes eventually evaporate. Permanence is not a feature of the universe. Impermanence is, change is, motion is. And yet that impermanence is not a flaw. It is the mechanism. It is the very thing that allows complexity to arise, that allows stars to form and explode and seed the galaxy with the elements that make planets and chemistry and life possible. If the universe were static, if nothing changed, if entropy were not always increasing, if energy were not always flowing from concentrated states to dispersed ones, there would be no stars, no planets, no chemistry, no life, no consciousness. The transience of things is the price of their existence. And it is, when you think about it clearly, a fair price. This is one of the things that cosmology does, that philosophy and religion have been trying to do for thousands of years. It puts human impermanence in context, not a context that diminishes it, but one that explains it. We are temporary because everything is temporary. We change and age and die because change and aging and death are expressions of the same thermodynamic principles that drive the evolution of stars and galaxies. We are not exceptions to the universe's rules. We are examples of them, and that means our transience is not a tragedy unique to us. It is a feature of reality that we share with everything that exists. There is something genuinely comforting in that, once you get past the initial chill of it. The universe is not singling you out for impermanence. It is not doing anything to you that it is not doing to everything. The sun will die. The Milky Way will merge with Andromeda. The last stars will burn out. The black holes will evaporate. Everything that currently exists will eventually not exist in its current form. You are in good company, and you are in a remarkably special moment in that company. Because you are alive now, in the stelliferous era, the age of stars, the epoch when the universe is full of light and energy and chemistry and complexity. You are not living in the cold darkness of the degenerate era, trillions of years from now, when the only things left are fading white dwarfs and silent neutron stars. You are not living in the heat of the universe's first moments, when it was too hot and too dense for atoms to form. You are living in what may be, from a certain perspective, the universe's golden age, the period when conditions are just right for stars to shine, for planets to form, for water to be liquid, for chemistry to be rich enough to support life, and for minds to exist that can look up and ask questions about all of this. That is not nothing. That is extraordinary, and it is easy to forget in the middle of ordinary life, in the noise and friction and difficulty of being human. It is easy to forget that this moment, this era, this epoch of cosmic history is genuinely remarkable, that the conditions that allow you to exist are neither guaranteed nor eternal, that they are the product of 4.5 billion years of planetary history and billions of years of stellar and galactic history before that, and 13.8 billion years of cosmic history before that. You are the current expression of a process that started at the Big Bang, not metaphorically, physically. The atoms that make you up have been on a continuous journey from the first moments of the universe to right now. Nothing about that journey was inevitable. Every step involved contingencies, specific physical conditions, specific events, specific outcomes from an enormous range of possibilities. The universe did not have to produce galaxies. Galaxies did not have to produce stars of the right mass to forge carbon and oxygen. Those elements did not have to end up in a solar system with the right architecture for a rocky planet at the right distance from its star. That planet did not have to have the right chemistry and the right conditions and for life to begin. Life did not have to survive the various mass extinctions and catastrophic events in Earth's history. The particular chain of evolutionary events that produced your species did not have to unfold the way it did. And yet here you are, the product of all of it, moving through the universe at over 1 million kilometers per hour, aware of your own motion, capable of understanding the physics that governs it, able to feel something when you contemplate the scale of it all. There is a word that keeps coming up when physicists and cosmologists talk about the nature of the universe in a broader sense, and it is a word that sounds unscientific, but that several serious researchers have used deliberately and carefully. The word is fine-tuned. The universe appears to be fine-tuned, not in a supernatural sense, necessarily, but in the sense that the fundamental constants of physics, the values that determine how strong gravity is and how strong electromagnetism is and what mass the electron has and how quickly the universe expanded after the Big Bang, these values appear to be set within extraordinarily narrow ranges that allow for the existence of complex structures, chemistry and life. If gravity were slightly stronger, stars would burn out too quickly for planets to develop life. If it were slightly weaker, matter would never clump together enough to form stars at all. If the cosmological constant, the value associated with dark energy, were even slightly larger than it is, the universe would have expanded too rapidly for gravity to pull matter together into galaxies and stars. If it were negative, the universe would have recoalesced long before stars could form. The actual value of the cosmological constant is so extraordinarily small compared to what quantum field theory naively predicts that it represents one of the deepest unsolved problems in theoretical physics, sometimes called the cosmological constant problem, or the worst prediction in the history of physics. These fine-tuning observations do not prove anything supernatural. They are consistent with several natural explanations, most prominently the multiverse hypothesis, which suggests that if there are vast numbers of universes with varying physical constants, it is unsurprising that we find ourselves in one with constants compatible with our existence, because we could not exist in any other kind. This is the anthropic principle, the observation that any universe we can observe must be compatible with our existence as observers. It sounds circular, but it is actually a meaningful constraint on cosmological theories. What the fine-tuning observations do suggest, regardless of how they are ultimately explained, is that the existence of complexity, of chemistry, of life, of consciousness, is not a trivial or inevitable feature of any possible universe. It is a feature of a universe with very specific properties, and we live in one of those universes. We are the beneficiaries of a set of physical parameters that happen to allow stars to shine, planets to form, water to be liquid, and carbon to build molecules of extraordinary complexity, whether that is luck, or necessity, or selection bias, or something else entirely. That is a question science has not yet answered. But knowing that the question exists, knowing that your existence depends on physical constants that could apparently have been otherwise, that changes how the universe feels. It makes it feel less like a given and more like something remarkable, something almost impossible that turned out to be possible after all. Now, let's talk about what is coming, because the picture of our motion through the universe that we have built over the course of this journey is already extraordinary, but it is incomplete. There are things we do not yet know, measurements we have not yet made, questions we have not yet answered. And the tools being built and deployed right now suggest that the next decade or two of astronomy and cosmology will be among the most scientifically productive in history. The Vera C. Rubin Observatory, currently completing construction in the mountains of Chile, will conduct what is called the Legacy Survey of Space and Time, a 10-year survey of the southern sky that will image the entire accessible sky roughly every 3 nights. Over its operational lifetime, it will catalogue roughly 20 billion galaxies and detect perhaps 10 million supernovae. The sheer volume of data it produces, roughly 20 terabytes per night, every night for 10 years, will transform our understanding of the large-scale structure of the universe, the distribution of dark matter, and the behavior of dark energy. It will map the cosmic web with a precision and completeness that no previous survey has approached. The Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, will combine the resolution of Hubble with a field of view roughly 100 times larger, allowing it to survey vast swaths of the sky with extraordinary detail. One of its primary missions is to probe the nature of dark energy, the force driving the accelerating expansion of the universe, by mapping the large-scale structure of the cosmos and measuring the barometric oscillations in the distribution of galaxies over cosmic time. If dark energy is not a cosmological constant but a dynamical field that changes over time, Roman is designed to detect that change. The Square Kilometre Array, or SKA, a vast network of radio telescopes being constructed across South Africa and Australia, will be the most sensitive radio telescope ever built, with a total collecting area of roughly 1 square kilometre and the ability to observe the universe across a huge range of radio frequencies. Among its many scientific goals, it will map the distribution of neutral hydrogen across cosmic history, effectively tracing the large-scale structure of the universe from the cosmic dark ages through the epoch of reionization and into the present, and will contribute to our understanding of gravitational waves, cosmic magnetism, and the early universe, and the next generation of gravitational wave detectors, including the proposed Einstein telescope in Europe and the Cosmic Explorer in the United States, both designed to be 10 times more sensitive than the current LIGO detectors, will open up a gravitational wave view of the universe that extends to almost its entire observable volume. These instruments will detect the mergers of neutron stars and black holes across billions of light years, building a statistical sample large enough to test general relativity at cosmological scales, to independently measure the Hubble constant, and potentially to detect gravitational waves from entirely new and unexpected sources. And there is the proposed LISA mission, the Laser Interferometer Space Antenna, a gravitational wave detector to be deployed in space, consisting of 3 spacecraft flying in a triangular formation with arm lengths of 2.5 million kilometers. LISA will be sensitive to the low-frequency gravitational waves that ground-based detectors cannot detect, including the waves produced by the mergers of supermassive black holes in distant galaxies, the kind of event that would have produced the final merger at the center of Milkomeda billions of years from now. It will also be sensitive to the stochastic gravitational wave background, a faint, pervasive hum of gravitational waves produced by all the mergers and interactions throughout the history of the universe, which may contain information about events in the very early cosmos that no other observation can access. These instruments, and others in development, represent humanity's ongoing effort to extend its senses beyond the limits of biology, to see further, hear more, measure more precisely, and understand more deeply. They are the continuation of a tradition that started when the first human looked up at the night sky and wondered what those lights were. From that first act of cosmic curiosity to the James Webb Space Telescope, from the naked eye to interferometry, from mythology to quantum field theory, it is one continuous thread of questioning, one long conversation between a curious species and the universe it inhabits. And the universe keeps answering, not always clearly, not always in the way we expect. Sometimes its answers raise more questions than they resolve, but it always answers. Every measurement produces data. Every observation constrains models. Every anomaly, every stubborn disagreement between theory and observation, like the Hubble tension, like the unexpectedly massive early galaxies Webb has found, points towards something real that we have not yet understood. The universe is not hiding. It is speaking in the language of mathematics and observation, and we are gradually, haltingly, but with increasing fluency, learning to understand what it is saying. And what it is saying, piece by piece, observation by observation, is this: you are not where you think you are. You are not as still as you feel. You are not as separate from the cosmos as you seem. You are part of a story that started before time as you understand it existed, and that will continue long after every star in the sky has burned out and gone dark. You are made of material forged in stellar furnaces and scattered by cosmic explosions. You are embedded in a web of motion so complex and so vast that a single human life is less than a heartbeat in its rhythm, and you are impossibly aware of all of this. That awareness, the capacity to know these things, to feel the weight of them, to be moved by them, that is the most remarkable thing in the observable universe. Not the scale, not the speed, not the age. The awareness, the fact that matter has organized itself here, on this small planet, in this quiet corner of the galaxy, into a form that can contemplate its own cosmic context. You are the universe becoming conscious of itself, and that is the answer to the question we started with. How fast are you moving through the universe? Fast enough to be somewhere you have never been before. Fast enough to never go back. Fast enough that every moment you exist is happening at a unique point in the history of the cosmos. And aware enough to know it, the universe is large. Our understanding of it is small. And the distance between those two facts, that is where the adventure lives. That is where the next generation of scientists will spend their careers. That is where the next breakthrough is hiding, in some anomaly we have not yet noticed, in some measurement we have not yet made, in some question we have not yet thought to ask. And that question might be yours. Let's end where everything begins, with a question, not a rhetorical question, not a poetic device, an actual, genuine, open question, the kind that sits in the chest and hums, the kind that does not have a clean answer and knows it, the kind that the best scientists in the world are actively working on right now in observatories and laboratories and on whiteboards covered in equations that most people will never see. The kind of question that, once it takes root in your mind, changes the way you look at the sky. Here it is. We know the universe is expanding. We know that expansion is accelerating. We know that something we call dark energy, something that constitutes roughly 68% of the total energy content of the universe, is driving that acceleration. We have measured it. We have mapped its effects across billions of light years and billions of years of cosmic history. We have built it into our models and our equations and our understanding of the large-scale structure of the cosmos. And we have absolutely no idea what it is, not in the way scientists sometimes say they do not know something when they mean they have not quite nailed down the last decimal place. In the way that means the thing doing most of the work in the universe, the dominant component of reality, is almost entirely opaque to us. We know what dark energy does. We do not know what it is. We do not know where it comes from. We do not know whether it is a property of space itself, a dynamic field that evolves over time, a consequence of quantum vacuum fluctuations, or something else entirely that we do not yet have the concepts to describe. It is the biggest open question in all of physics and cosmology, and it has been sitting there, unresolved, since the discovery of cosmic acceleration in 1998. The people who discovered that acceleration, Saul Perlmutter, Brian Schmidt, and Adam Riess, received the Nobel Prize in Physics in 2011. Their discovery was that distant Type Ia supernovae are fainter than they should be if the universe were expanding at a constant rate or decelerating under gravity. The universe is not slowing down, it is speeding up. The expansion is getting faster. And whatever is making it faster is something that has negative pressure, something that behaves in the equations of general relativity like a kind of anti-gravity, something that pushes space apart rather than pulling it together. Einstein himself, decades earlier, had introduced something very much like this into his equations, a term he called the cosmological constant, a kind of energy density of empty space that would counteract gravity and produce a static universe. He later called it his greatest blunder, after Hubble's observations in the 1920s showed that the universe was expanding rather than static, and the cosmological constant seemed unnecessary. But the universe, it turns out, does have something very much like a cosmological constant. Einstein's blunder may have been calling it a blunder. Whether dark energy is exactly equivalent to Einstein's cosmological constant, a fixed, unchanging energy density of the vacuum, or whether it is something more dynamic, something that varies over time and space, is one of the central questions that the next generation of cosmological surveys is designed to answer. If dark energy is constant, the universe will expand forever, growing cold and dark over trillions of years, ending in the quiet inevitability of heat death. If dark energy grows stronger over time, the expansion will accelerate without limit, eventually tearing apart every structure in the cosmos in the Big Rip. If dark energy weakens or reverses, the universe could recollapse. The ultimate fate of the cosmos depends on the answer to a question we cannot yet answer. And dark energy is not alone in its mystery. Dark matter, the invisible non-luminous substance that accounts for roughly 27% of the universe's total energy content, is similarly opaque. We know dark matter exists. Its gravitational effects are unmistakable and have been confirmed by multiple independent lines of evidence: the rotation curves of galaxies, the bending of light around galaxy clusters, the large-scale structure of the cosmic web, the acoustic oscillations in the cosmic microwave background. Dark matter is the scaffolding around which all visible structure in the universe has assembled itself. Without it, galaxies as we know them could not exist, but we have never directly detected a dark matter particle. Every experiment designed to catch one, and there have been many, some of extraordinary sensitivity, buried deep underground to shield them from cosmic ray background, has come up empty. The most popular theoretical candidates, called WIMPs, weakly interacting massive particles, have not been found despite decades of searching. The search continues with increasingly sensitive detectors and new theoretical ideas. Axions, another candidate, far lighter than WIMPs, are being searched for in dedicated experiments. Primordial black holes formed in the early universe before any stars existed, have been proposed and constrained by observations. The identity of dark matter remains unknown. So here is the situation as we actually stand right now in the early decades of the 21st century. We have built a cosmological model, lambda CDM, that successfully describes the large-scale structure of the universe with extraordinary precision. It predicts the distribution of galaxies across cosmic scales. It matches the temperature fluctuations in the cosmic microwave background. It correctly describes the abundance of light elements produced in the first few minutes after the Big Bang. It is one of the most successful scientific models ever constructed, and 95% of its content, dark energy and dark matter combined, is stuff we do not understand. The model works. Its ingredients are mysterious. We have mapped the universe with extraordinary precision, and most of what we have mapped is invisible to us. That is not a failure, that is progress. A century ago, we did not even know that other galaxies existed. We thought the Milky Way was the entire universe. We had no idea that the universe had a beginning, a finite age, a history that could be traced. We had no concept of dark matter or dark energy, or gravitational waves, or the cosmic microwave background, or cosmic inflation. The universe that science has revealed over the past 100 years is immeasurably richer, stranger, and more vast than anything any previous generation could have imagined, and the same will be true of the next 100 years. The anomalies we are currently wrestling with, the Hubble tension, the unexpectedly massive early galaxies revealed by Webb, the identity of dark matter and dark energy, these are not embarrassments, they are invitations. They are the universe telling us that the story is not finished, that the model needs to be extended, that somewhere in the gap between what we expect and what we observe, there is new physics waiting to be discovered. New physics that might reveal things about the nature of space and time and matter and energy that would change everything we think we know about our motion through the cosmos. New physics that might answer questions that currently have no answer. New physics that might make the picture we have built over the course of this journey look like what Newtonian mechanics looks like in the context of general relativity, correct within its domain, but incomplete, a special case of something deeper and stranger and more beautiful. And here is the thing about that. The people who will discover that new physics, the people who will look back at the anomalies of the early 21st century, the way we look back at the anomaly of the Michelson-Morley experiment in 1887, which undermined Newtonian mechanics and pointed the way towards special relativity, those people might be watching this right now. The next Einstein, the next Hubble, the next Planck, they are alive today. They are children or students or young researchers. They are looking at the same night sky you look at, asking the same kinds of questions you ask when you let yourself really think about what is out there. They are going to carry this story forward in ways we cannot predict, and the universe they will describe will be even more astonishing than the one we currently inhabit. That is not hyperbole. Every generation of scientists has discovered things that the previous generation thought were unknowable or impossible. The universe has consistently turned out to be larger, older, stranger, and more intricate than anyone expected. There is no reason to think that pattern will not continue, and what does all of that mean for you right now? Moving through the cosmos at over 1 million kilometers per hour on this small blue planet in the outer arm of the Milky Way, it means that the question we started with, how fast are you actually traveling through the universe, is not a question with a single clean answer. It is a question that opens up into other questions. questions about the nature of motion and reference frames and the relativity of velocity, questions about the structure of the galaxy and the dynamics of superclusters and the expansion of space, questions about dark energy and dark matter and the ultimate fate of the cosmos, questions about the origin of life and the rarity of consciousness and the fine-tuning of physical constants, questions about what it means to be a temporary assembly of ancient atoms moving through a universe that will outlast everything you will ever know, aware of your own motion in a way that most of the matter in the universe is not. These questions are connected. They are all part of the same question, really. The oldest and most fundamental question there is, where are we? And the answer, insofar as we have one, is this: you are on a planet spinning at roughly 1,670 kilometers per hour at the equator, orbiting a star at 107,000 kilometers per hour, in a solar system sweeping around the galactic center at 828,000 kilometers per hour, in a galaxy moving toward the Great Attractor at roughly 600 kilometers per second as part of the Laniakea supercluster flow, in a universe whose expansion carries the most distant observable galaxies away from us at speeds that exceed the speed of light, in a cosmos that began 13.8 billion years ago, in an event whose nature we are still trying to understand, that has been expanding and evolving and building complexity ever since, that will continue to expand and evolve for trillions upon trillions of years into a future so vast it makes the present feel like the very first breath. You are, in total, moving through the universe at a speed that depends entirely on your reference frame, because there is no absolute rest, no fixed background against which all motion can be measured, only the relative motion between observers. The most meaningful reference frame for measuring our total motion is the cosmic microwave background, the afterglow of the Big Bang, which fills all of space uniformly and represents the closest thing to a universal rest frame that exists. Relative to that background, the solar system is moving at roughly 370 kilometers per second, about 1.2 million kilometers per hour, in the direction of the constellation Leo. 1.2 million kilometers per hour, every minute, every second of your existence. You have been moving at that speed since you were born, since your parents were born, since the first human stood upright on the African savanna and looked up at the stars without yet having the language to ask what they were. The planet has been moving at that speed for 4.5 billion years. Before there was any life here to feel it, you feel none of it. You sit still, or you walk, or you drive, and the universe carries you along at a speed that would take you from one side of Earth to the other in about 33 seconds, and you feel nothing. No wind, no pressure, no sense of motion. Just the ordinary sensation of being alive in a body on a planet, the larger motion completely invisible to every sense you possess. And yet it is real, more real than anything you can directly perceive. The instruments we have built, the telescopes, the interferometers, the gravitational wave detectors, the particle accelerators, have revealed a universe that is operating at scales and speeds and depths of complexity that our nervous systems were never designed to detect. We are not built to feel the spin of the Earth or the orbit of the solar system or the flow of the Milky Way through the cosmic web. We are built to navigate the surfaces of planets, to find food and shelter and connection, to live out our brief lives in the narrow band of scale between the very small and the very large where biological existence is possible. But we are also built, uniquely, as far as we know, to transcend those limits, to build instruments that extend our senses beyond their biological range, to construct mathematical frameworks that describe realities our intuitions cannot grasp, to sit here and understand, genuinely understand, that we are moving through the universe at over 1 million kilometers per hour on a journey that has no final destination, embedded in a cosmos of almost incomprehensible scale and age and complexity. That understanding, that reach beyond the biological, is the most distinctively human thing there is. More than language, more than tools, more than social organization, the drive to understand the nature of reality, to ask not just how to survive, but what the universe is and how it works and where we are within it. That drive is what makes us something new in the history of the cosmos, not the most powerful thing, not the most durable thing, not the largest or the fastest or the most energetic thing, but possibly the most aware thing, the thing that knows where it is. So the next time you step outside at night and look up, and I hope you do, I hope this has made you want to, remember what you are doing. You are not just looking at the sky. You are a point of awareness in a moving, expanding, 13.8 billion-year-old universe, looking outward towards structures of incomprehensible scale and age and strangeness. The photons hitting your eyes left their sources years or centuries or millennia or millions of years ago, traveling across expanding space to end their journey in your retina at this specific moment in cosmic history. You are receiving messages from the deep past. You are seeing the universe as it was, stretched across time all at once, and somewhere out there, in the dark between the galaxies, in the microwave hiss that fills all of space, in the gravitational whispers of colliding black holes, the universe is still speaking, still evolving, still building towards something, or dissolving towards something, or cycling back towards something, in ways we do not fully understand. Still full of questions that have not been asked yet, and answers that have not been found, the question of how fast we are traveling through the universe turns out to be a door that when you open it leads to rooms you did not know existed. Rooms full of dark matter and dark energy and gravitational waves and the fine-tuning of physical constants and the far future of the cosmos and the origins of life and the nature of consciousness. Rooms that open onto other rooms, a house with no final wall. That is what science is, not a set of facts to be memorized, a set of doors to be opened, and behind each one not a conclusion, but a view of something larger, stranger, and more beautiful than what you could see before you opened it. You have been moving through the universe your entire life. You will keep moving through it for as long as you live. Every moment you exist, you are somewhere new, a unique point in space and time that has never existed before and will never exist again. The universe will continue long after you are gone, carrying on its vast, relentless, beautiful motion without you. But right now you are here, moving, aware, asking questions. And that, in a universe that has spent 13.8 billion years building toward the capacity for exactly this kind of moment. That is not a small thing, that is everything. If this journey through the cosmos left you with something, a sense of wonder, a new question, a feeling you want to hold on to, then share it. Because curiosity is contagious in the best possible way. The more people who look up and ask what is out there, the richer the conversation gets. The more eyes on the sky, the more minds working on the questions, the faster the doors get opened. Science is not a spectator sport. It is something you participate in every time you refuse to accept a shallow answer and push for a deeper one. Every time you look at something familiar and ask why. Every time you let yourself be genuinely astonished. The universe is astonishing. You are part of it, and you are moving through it right now at over 1 million kilometers per hour. Welcome to the ride. And if your mind is still racing after all of that, I have got the perfect next video for you. Check out the video on your screen to explore how long it would actually take to travel 1 light year. Trust me, the answer is not what you expect. See you there.